Just testing audio. pleasure. It's not just formal to say that. It's really a pleasure for me to host again this small informal meeting that is growing a little bit year by year. So this year we are having these research jam sessions for the fourth time. It is about interaction between humans and robots. Steinbeck in the 40s didn't know much about gender equality and respect, so he used of mice and men, and we now have I still have these robots and men. It is not intended to be diminishing to anybody. We have a wonderful set of speakers this time. You know, the philosophy of the jam session is that this time of the year, by some stellar astral connection, we have people that are around Pisa, and we try to intercept as many of them as possible and just cast a casual meeting together. Now the quality is always increasing, and also the number of people attending are more and more, because we have such distinguished guests. This is the program. We have no time because, of course, we are already a bit late. And let me just make by way of introduction. One of the reasons why we have these people is that tomorrow we will have a review, the final review of a project, the Hand Embodied, that is finishing this year. So we have some of the participants to these meetings that are here in Pisa, and also some of the reviewers who are very distinguished speakers today. But also we had earlier today, the discussion of the PhD defense of two of our students, and the members of the committee are also here. So let me just, for those who were not at the discussion of the PhD students this morning, just share with you what they did. One of the topic of our own lab is concerned with the evolution of robotics and with the evolution of the muscular system of robots, if you want. On one side, you know, yeah, there is too much light. On one side, you know, machine intelligence has made a tremendous progress in the last 40 years or so. Some time ago, we had the Puma 560 that had 160 kiloflops, and now in the dumbest smartphone, you have gigaflops, 40,000 times the intelligence in the machine. If you look at machine motion instead, well, the Puma had big controllers on one side and had servo motors. And if you look at the picture in robotics in 2010, then, well, you still have servo motors. Nothing has changed until, I would say, rather recently. There is, in the last 5 years, I would say, a lot of interest, or 5 to 10 years, a lot of interest in an evolution of actuation. From the rigid actuation of servo motors, we have been moving to torque-controlled actuators. Here is a picture of the famous DLR torque-controlled actuator. Then series elastic actuators, and more recently, variable stiffness and variable impedance actuators, which are some of the themes that the work of our students revolved around. In Pisa, we have been doing this, and IIT, we have been doing some of this research recently until these are the different prototypes. And the next topic, since we now start to have around the world a few of these robot muscles, if you want, is what are they good for? So, of course, we can come up with some ideas about using the one single degree of freedom or more degrees of freedom. Here the DLR variable stiffness arm and system is shown. And there are applications that we know where robot muscles, robots that can change the stiffness, robots that can, or soft robots, if you want, can be applied in locomotion, manipulation, and so on and so forth. But what are the real killer applications? What will change the scene? We suspect that there is more, a wider range of applications that few researchers alone can explore. And that the idea came of crowdsourcing the exploration of new territories. So basically, we would like to make variable stiffness or soft robots more widely available to people, even outside this research community, even to amateurs, practitioners, to make them, to use them and come up with new ideas. So one of the contributions of Manolo Garbini, who
So I'm very pleased to be here, finally. I've been working as an external reviewer to THE project, the hand embodied, in the last 4 years. And Antonio is, of course, principal investigator of this group research efforts. And I'm here in the basement of this THE project, I think. So my title is Mechanical Impedance and Brain Dynamics Matching between Human and Robot. So if humans physically interact with humanoid robots or exoskeletons, I think impedance matching and dynamics matching are really important. And I think this is low joint stiffness mode, which we have only 50 Newton meter per radian. And now it's quite compliant. You could see that we have let the low air pressure, so it is. Okay, this is a work by Dr. Ugulu and Noda and Morimoto. So we believe that we need to have mechanical impedance matching between human and robot. Human body can generate large force with relatively low mechanical stiffness. This has been established now for almost 20 years. And reduction geared power suits, which is very popular in Japan, can generate only small torque, or it could be very stiff with high reduction gears. In contrast, hydraulic exoskeleton robots, which have been developed mainly in the US for military purpose, is very, very stiff when valves are closed. So we believe impedance matching is necessary for safety, comfort, and efficiency of interaction between exoskeleton robots and human body. And intrinsic time constant can be defined as square root of inertia divided by stiffness. This defines a natural mechanical frequency in which our body is oscillating. When we plot this intrinsic time constant defined by square root of inertia divided by stiffness, for hydraulic actuator with valve closed, it's really low. And that means very high frequency. And for electrical motor with rigid brake or high reduction gear, it's really low. But series elastic actuator, you have much nicer range. And for our pneumatic and electrical hybrid actuation system, we cover this range. And human static time constant, human dynamic time constant, which are measured by us, probably this is 1997, it's even larger, means more compliant, more longer time constants. So that's the reason why we picked up this pneumatic and electrical hybrid actuation system. We used this system also for the upper exoskeleton robot for rehabilitation purpose. In this case, we have mulch joint arm movement. And yes, this can do gravity compensation at the shoulder and elbow. Whether we have here, again, some kind of mannequin upper and lower arm and the hand, but actually we put stroke patients' hand and arm within this system. Here, we further can measure EMG and to estimate the joint torques generated by muscles, and we added on this robot. But we didn't implement any mechanical impedance estimation and mechanical impedance control as Rush and other colleagues here did. In addition to this mechanical impedance matching, we believe brain dynamics should be also matched between robot side and the human side. So human exoskeleton interaction contains at least 4 components: human body, human brain, robot body, and robot brain. Brain-machine interface-based robot control introduces direct brain-brain interaction in a sense. From human brain, we measure brain activity, and we influence robot control software based on this brain activity measurement. So feedback gains should be matched, for example, between humans and the brain. And central pattern generator dynamics should be matched, or learning dynamics on both sides should be matched. Otherwise, you are dealing with much faster mechanical dynamics or much slower mechanical dynamics, or central pattern generator with different frequencies can be in very bad, unstable modes. So with this in mind, we've been trying to change both subject learning and the robot control. And we had some success to adjust robot control system based on EEG measurement. But I think this is really complicated story because brain dynamics is complicated, of course. Human body is very complicated nonlinear dynamical system, which could be unstable. And control of the exoskeleton is a headache. And EEG measurement is very, very noisy. Still, we believe that somehow integrating all these four components in a stable and controllable manner is the only way to utilize exoskeleton robot for rehabilitation, posture control, and locomotion. So this is interesting not only from clinical and rehabilitation objectives, but also from neuroscience objectives. Our group has been developing a method called decoded neurofeedback, in which you have some lesion of interest in the brain. And the objective is to somehow spatial temporally control the brain activity within that specified area with a technique called decoding information from the brain and real-time fMRI neurofeedback. But currently, we use just visual feedback to control the brain activity, which is quite indirect and weak in influencing the spatial temporal dynamics of the brain. Suppose that if you have nice whole body exoskeleton robot, which can influence the human body with position, pose, tactile sensing, audition, and vision, we probably have the best system to connect human body, robot body, human brain, and the robotics brain in the most intimate and powerful way. So I think this kind of robot and human interaction are not only important for clinical rehabilitation purposes, but also for fundamental understanding of the brain dynamics or how our brain works. So I think that's all what I'd like to tell you. Thank you.
Thank you. Time for one or two questions?
Yeah. Thank you very much for a very inspiring talk. I just have a question. You were focused on human studies. I guess that studying brain dynamics could be much easier to perform in animal studies, where you could, for example, substitute all periphery sensors and actuators with either models or some physical or simulated models. Is any activity of this kind being carried on in your institution, or are you aware of it being done somewhere in the world?
Yeah, that's true. For animals, you could utilize more invasive method, for example, stick electrodes to measure electrical activity of neurons, or you can cut down some portion of the brain and see its effect. But recent progresses of decoding method in fMRI, and it's also expansion to the so-called neurofeedback, is quite appropriate for human. study. Because for humans, if you utilize 3 Tesla fMRI, you could measure, say, 10,000 boxers activity simultaneously. And if you utilize a technique called merge boxer pattern analysis, MEPA, you can extract information like orientation of the grading which our subject watch, or reconstruct black and white general images, or even dream reading during hypnagogic image. But if you would like to apply these techniques to animals, you first need to train animals to do, several cognitive functions. So at present, I am more inclined in working at quite abstract level of brain dynamics, which can be measured by fMRI and can influence brain activity through several types of neurons. But of course, animal study is so important and so fundamental. So in the future, we would like to combine G's. But that means we should probably be able to do fMRI neurofeedback even for animals, like say macaque monkeys or marmoset monkeys and so on and so on. And that's a future direction, I think.
Thanks for a great talk. So, with invasive BMI, you have 2 schools of thoughts. One that has a fixed decoder and forces the brain to adapt to it, or the other way around. So, with your EEG example, do you use what kind of approach do you use? Do you have an adaptive decoder, or?
In the non-invasive brain-machine interface literature, we have the terminology called co-adaptation. It is well known that for BMI application, human brain or animal brain adapts to the new environment. But at the same time, you can change decoder of the brain activity with some learning algorithms. Or you can even change the control strategy of the controller of the robot in accordance with human adaptation. So we are really interested in this co-adaptation of human brain and the robot brain.
Coming to that. Thank you very much for the invitation and the introduction. So what we do, I put under the umbrella human robotics. So we use robotics to understand human motor control, and also we use motor control and robotics to develop devices to help people. So for example, this robotic wheelchair with cerebral palsy subject. So the approach we have is that, so we do motor control experiments, computational model hand in hand. So when you find something you may want to understand, so developing a model to understand what you found, and it's giving you questions that you can test with experiments. So we have various applications. So for example, this brain control wheelchair that we did about 10 years ago, training for microsurgeries where you want to replace training on rats by training on a virtual reality workstation, and also robot-assisted rehabilitation. We work especially in the rehabilitation of the hand function. And so I'm coming to the real thing. Okay, so this is a work that we did with Ganesh, Atsushi, Mitsuo Kawato, and myself, and a few other people. And the Japanese is this one, in fact, student. And okay, so the point is that, so contact you have from the very beginning. And physical contact you need to work together in many daily action. You need for dancing, you need for fighting also. It's very important to understand physical interaction for rehabilitation, for physical rehabilitation. And finally, children have a lot of physical contact for some reason. Okay, so physical contact, so there is probably some communication. Communication has been studied a lot for language, of course, also for gestual language, gestual communication, very, very little, on the other hand, on haptic communication. So that's what we are interested in. So we have developed an experiment that you see here. So you have two people in the same room. So this is a setup that is at ATR by Professor Cavato, and so you can connect the two people. So they each have his robot, and they can be connected haptically as you want. So you can program the connection as you want, and then you can systematically investigate how they work together or do not work together. So this is the task that we gave. So you have to track a target. You just have to track a target. It's moving pseudo-randomly. And so you want to see, so each of them has the same target, and in some trial they are connected. In some trials they are not connected, so they are connected for 60 seconds and then not connected, and then not connected again, and then connected random. And then what is important is that you have a compliant connection. So why is that important? Is that because you don't have to follow. So if you follow, it is that you coordinate in some way. So on the other hand, if you have a stiff connection, then you have to follow because, yeah, that's clear. So if you have a compliant connection, you don't have to follow, so you can look for evidence of coordination. What is amazing is that, so you have people in the same room as you see, so you have the subjects, they enter at the same time, and basically if you ask them after the experiment, so the force you felt sometimes, what was it? In fact, only 2 of about 100 found out that they were connected. For other people, they don't care, they don't know what was the connection. Another thing that is surprising is that you ask them, so did this force help you or did it disturb you? And then all of them, they say it did disturb me. However, it is helping. So you see that. So this is a measure of the tracking error, and you see how you improve with time. And this is in disconnected trial. So you have trial when you are connected and trial where you are disconnected. So this is the error in disconnected trial. So when you are alone, but you have been connected together before. And you compare to people who train without any connection, but at the same time. And you see that you learn better by having been connected. So that's important. So you learn better by having been connected. Now let's analyze this learning, so or this performance improvement when you are connected. So we plot. So this is again the tracking error. So there's an index of the tracking error. So here it is helping. The connection is helping, and it is damaging. And what you see is that when the partner is better, then you improve with the partner. It's logical. You just improve with a better partner. What is more surprising is that when the partner is worse, you improve as well. So you improve anyway. So whether the partner is better, okay, logical. When the partner is worse, you improve also with the partner. Now, the question is, how can we explain that? So one possibility is that, in fact, you do not coordinate at all. Each of the subjects is doing his job, and then you have the mechanical connection, and then you would improve in this way. So this would be this coactivity, right? I mean, in this example, maybe you have the impression that they work together, but in fact, each of them may work for himself or herself. And however, such coactivity, what it would predict is improvement, so basically averaging between the two subjects. So if the subject is better, you would have half of the advantage, and if the subject is worse, you would be less good. So from that, we know that it is not possible. There is coordination between the two subjects. Now, we looked for other explanation. For example, you would increase attention because you have no force, and suddenly you have force. Maybe you can concentrate better when you get the force. Or maybe you could switch to the better. So you would have a mechanism to detect who is better and online, and if the guy is better, then I follow the guy. If I'm better, I want to be still. Okay? So both cases we can test by an experiment where we use the force we coded in another pair. So we use the force and we connect this subject with the force of that one, this subject with the force of this one. Okay? So we tested this with a few subjects, and this is what we found. So you see that you have deterioration overall. So it's just like adding noise. So it's not, attention is not enough, and you do not switch between the better or the. Okay, so now another possibility would be that you have just multisensory combination. You have vision, you see your target here, and you have a haptic connection. You are related with the robot to the other. So maybe you may combine this visual information with the force information and make the best of it. And to test that, we developed an experiment where you are connected to the trajectory of somebody who did the experiment alone. So both are connected to another subject who did the experiment before alone. And so if it is only the combination of visual and haptic information, it would make that you could behave as with a human subject. So when you do that, what you find is that when the partner is better, you improve with the partner, but when the partner is worse, you deteriorate with the partner. And in any case, the improvement with the partner is less than with when you interact bilaterally with another human subject. So multi-sensor integration cannot explain this result. So of course the question is, so how does it work? How could it work? By which reason? So it's not coactivities. It means there is a coordination mechanism. This we know, we have learned. Increased attention is not sufficient to explain. We cannot switch to the better. It doesn't work. It doesn't explain our result. And finally, integration of vision and haptics is not sufficient to explain this. And okay, so when we look at the flow of information between the two subjects, we see that so when you have no interactions and both have an action, no feedback between them. When you have trajectory guidance, so this one is able to react to the action of the other one, but this one cannot react to this one. So what produce the benefit of the interaction is the possibility of both to react to the partner. So that's what we learned from this experiment. So when both have action and reaction, they improve each other continuously. Now another experiment that we did in London more recently, it's a very new experiment. So we want to understand how the stiffness of the connection is influencing the behavior. So whether you have a table that you carry together or whether you have a pillow, you behave the same, and how would you adapt in both cases. So we have this interface in London. So this is just for width, flex, and extension, and we can change the stiffness, and we can measure the muscle activation very precisely. With the previous setup with two-dimensional movement, it's a bit too complicated to infer the muscle activation exactly. So you have this experiment here. You can see how you follow the target. You can also manipulate the amount of noise with visual feedback. Here you have for two people. You see that they are separated by a curtain. They are also separated for the noise. And so they do the same task. They track a random target. They are connected by a spring, and you change the connection stiffness from compliant to rigid. And so here you see the performance again. So the improvement of performance, whether the partner is better or whether the partner is worse. And you see that with a rigid connection, you improve with a better partner, but you deteriorate with the worst partner. That is logical because you have to follow half. Now, when it is compliant, we have the behavior that we saw before. Maybe you improve not as much as with a better partner than when the connection is rigid, but you improve also with the worst partner. Now, what is interesting is that with this setup, we can look at how you change your muscle activation. And so this is what we analyze here. So this is, again, analyzed for a better partner, for a worse partner. And you look at the change of EMGs, so muscle activity. And you have the reciprocal activity in solid color and the co-contraction in the pale color. What is really interesting is that you see that when the connection is rigid, you relax with a better partner. When the connection is rigid, you have, if you are the better partner, if the other partner is worse, you have to co-contract and to produce also more reciprocal activation. So basically, with a rigid connection, you take the lead when you are worse, and you follow when you you follow when you are worse, and you take the lead if you are better. Okay. So what is really interesting is that it means that so you are able to infer online who is better and adapt to that. So online, you don't know that you are connected to the guy, but you adapt, you infer the performance of this connected partner, and if the partner is better, you will follow. If the partner is worse, you will take the lead. And you adapt the force and the impedance according to the condition and also according to the partner. So in summary, so we have discovered an involuntary coordination mechanism that enable connected partner to improve from each other. And this mechanism requires active partners to manifest, otherwise it doesn't work. And the partners are able to identify the relative performance and some features of the partners, and to adapt both force and impedance to control optimally with the connected partner. And that's the end of my talk. Just one more. So what can we conclude from that? So this suggests that now that we know that you work better with a partner, maybe we could use this property to develop better therapy protocol, and also better robots. So we can make robots reactive as humans are, so as to get advantage of this communication to the haptic channel. And finally, so one possible explanation that children play together many physical games, maybe, of course, they play because they play, but perhaps it's helping them learning better. And that's the end of my presentation. And just some advertising. So we have some postdoc and PhD position for collaboration with Santa Lucia Foundation on lower limb exoskeleton for spinal cord injury patients, and also for impedance control for industrial finishing tasks with a colleague in Singapore, if you know somebody.
Hello, and thanks for your talk. I'll be very quick. First question is, did you try to test a person when being helped by his own recording of a previous test instead of someone else, to see if there is an interaction between kind of approach to solving the problem? And the second one, did you try, instead of a person, a control algorithm as partner? Okay.
So I start with the second one. And we have tried many different possibilities. So, for example, so I show you. Yeah, so this is classical guidance from a robot, right? So we have connected directly with the robot, and what you see is that you improve, but you improve less than with a human partner. Okay, I don't think we have tried with your trajectory or your force of before. I don't think we have tried that. We have tried also with experts, so with people who have done the experiment many, many times, and it is less good than when you work with somebody who has the same knowledge than you, approximately. Yeah.
Have you done a frequency domain analysis of the results? Do you know what happens when people are improving? Are they improving the low frequency response or the high frequency response?
Thank you. Yes and no. So let's say no. We have done a frequency analysis for the two-DOF experiment, and at that time we didn't find anything very clear. However, it's very difficult for the two-DOF experiment. So we should redo them on the one-DOF experiment where we may see something.
If there is time, of course. Well, since I'm interested in designing, let's say, control system that help haptically people perform tasks, do you think that there is a way to exploit your results to better design a control system that helps better?
Yes, we have done it actually. And so if you use a proper control with a robot, you can get similar effect as with a human. Yeah.
Okay, I think we'll finish up there, just to try and stay a little on time, or a little less far behind time. Thank you very much. Okay, I think we're almost ready for our next presentation. Okay. Yes. Okay, so third presentation is by Rod Gruppen from the University of Massachusetts, and this is on belief space manipulation.
Well, it changes that a little bit, but since it's use that. Should I use this?
Oh, that's right.
Can you hear me back up? Speak up. Oh, okay. So I decided to talk about dexterous manipulation. I'm going to define a different kind of definition of dexterous that goes back a long time, but is not typically what you'll hear when you hear a roboticist talk about dexterity. I'm going to put some old ideas together with some new ideas. This is a jam session, so I'm going to present some stuff that it might be exciting in the future, but doesn't have a whole lot of support yet, and I'll show you some results, and we'll go from there. So one of the definition of dexterity that I enjoy the most is due to Nikolai Bernstein, who was he coined the term biomechanics, and he was a neurophysiologist. The idea is that dexterity down here, he studied lots of stuff that had to do with the compositions of motor behavior. He did it in the labor force by taking time exposures and watching the dynamics and tried to evaluate how repeatable they were. But the idea is, let's see, this thing works like that? Yeah. So his definition, I paraphrase down here at the bottom, is the ability to sort through an infinite variety of potential solutions to solve new motor problems quickly, correctly, rationally, and resourcefully. So this doesn't necessarily mean your right hand as it might in the dictionary. It means everything that has to do with motor control when you're confronted with a new situation. So here is a more old work, which I also find inspirational. The first was Wolfgang Kohler, who is an experimental psychologist and worked with animal behavior. I'm going to show you an example. The second is J.J. Gibson, which more people know about, and the concept of affordances. And so I'm going to try to show you what both of these things mean in the context of this little video. So this is a chimpanzee faced with trying to get that banana. The chimpanzee obviously knows things like banana and leaping, but it also knows other things, boxes for instance, and it can grasp them, it can push them around, it can drag and roll them. These are the things that a box affords, and the chimp is right on. You can see him working it out. This is actually her, not him. Working it out, looking at the banana, looking at the resources in the environment, trying to figure out what they afford and what it might do with it. And 2 boxes might be better than 1, so maybe that'll help. No, throwing didn't really help, but he does know boxes in terms of all of these different opportunities for action. Eventually it gets stacking and leaping, and there's really remarkable examples that are even more clever than this. One of the things that I looked at here is that represents a representation of a box. It's not Euclidean geometry, it's not algebraic surfaces. It's all the things that the animal can do with that, and when they might come in handy is dependent on what the runtime environment looks like. So these are skills. What we thought when we look at examples like this is that there are possibly native or prior skills and representations that define the object in terms of applicable skills. So I'm trying to solve a new problem. I survey the environment. I find out what all these things might do to help me solve it, pick the one that's most likely, and then try to solve the problem. I always think of the cases when I'm coming into my garage after work and I flip on the light switch with the same finger almost every time. But if I happen to have gone grocery shopping, I might have groceries and I'll flip it on with my elbow. And I'm pretty sure I could do it with my shoulder, probably my foot if I really had to. Nose, I won't do it with my tongue even if circumstances demand it. But it's possible, and how do I know that? Because I've never done some of these things before. So we'd like to see whether or not we can come up with robot systems that can do the same thing. We start with motor primitives, and this is a classical example. Classical goes back to 2003. of a motor unit that's used often for policy iteration in machine learning techniques. It's due to Stefan Shaw, very common, you probably all know this work. The first term there in the blue box is a PD controller. It's just got a proportional and derivative term, so that's very standard, and we're gonna use that. The second term is some additional terms you can use to deform the field. This might be a Hooke's law field. You can deform the field by putting together a linear function approximator, a nonlinear function approximator. It's just a weighted sum of possible other motion profiles you know about. The last one's a coupling term, so you can hook things like planners and other influences into the behavior of the system. It's very successful. Does all kinds of beautiful work in adaptive robot control when you learn from a human being, for instance. Based on these ideas of a landscape of attractors and optimal control framework, you can produce adaptive optimal controllers. And it can generate a sequence of kinematic goals that you then feed to the motor units below this level of reasoning. The things that we didn't want with respect to dexterity and studying that is that it requires a fixed plant. It knows what sensory and motor resources it has already, and it uses them. A particular task doesn't just address any task. The function approximators make it specific, and fully observable environments. X is the kind of a time. It starts at 1 and it goes to 0 at the termination of the episode. Y is the state. It's a differential equation, yes, but X is just a way to turn off when you get to the goal. Okay, we stripped off, we have the first term, we got rid of the linear function approximators, we allow a different mechanism for coupling that's based on straightforward Moore-Penrose-based null space compositions instead. But this is actually an older idea called the control basis that we've been using for a while. And basically the potential that Hooke's law I referred to before could be the phi. You're allowed to use other things, they must be navigation functions so that you can guarantee that greedy descent of the potential will get you to a goal. And then you can combine them in combinations that are formally correct. Sigma and tau are just resource assignments. They're sensors and effectors. We want to be able to switch those if we encounter new problems, like trivially left to right hand. We also look at the state feedback from the dynamic response of this system. So we hook it to the environment, it starts doing a dynamic response. If the reference feature encoded in sigma is not available, or we haven't run the controller yet, we don't know what its state is. Maybe we elected not to save CPU cycles or something. If the reference sigma is not available, we give it a dash. If it's in a transient response, it gets a 0, and if it's a 1, it's converged. We've used, much more sophisticated dynamic feedback, but this really does pretty well. We built all kinds of controls based on this really old work. In a four-legged walker. And it learned in 10 minutes to do a rotate gait that you see here. And on the left over here is the program it wrote. It uses 5 bits of feedback from controllers that it could have run by assigning resources to potential fields. It measures state that way, and then it switches through different controllers. The controllers are listed over here in this too small t, and they're a little bit more complicated, so it doesn't really matter. But it entered into this cyclic 4-legged walking gait. This program also runs on this hand. It's a similar robot. It has 4 fingers instead of 4 legs, and it actually moves the world rather than the world moving it, so to speak, in the case of the walker. But it generalized. This was what we were after. We're after a system that said if the kind of idiosyncratic relationship between the robot and the environment is satisfies the underlying assumptions, then it will run. It will do something useful, and you can use that in another context. All right. So there's a counterpart to this thing that I call track, and it's a search controller. And this is a more contemporary idea, is the application of this. We run the same thing, except for sigma, we substitute, instead of the signal from the environment, we substitute a probability distribution that summarizes where that signal was found in the environment before. All right? So the U sub t there is some kind of reference input to the motor units beneath us. It's very important because it allows us to orient to the environment. So coffee cups are often found on tables, and I can encode that very easily in such a model. There's some examples. This was Steve Hart presenting objects to our robot Dexter, which was a large humanoid, bimanual humanoid. And the distributions over there are that it's a fixed robot. So the distributions over there describe pan and tilt angles, where it's likely to find saturated cues or motion cues. Below is the occupancy grid of a room, and the traces you see are the positions where humans have been seen in the context of some task they were performing, in particular searching for an object. On the left it was a book, and on the right it was a clamp. They're found in different places, so the human went to different places and went there in different sequences. And so by watching the temporal history of a human being, you can predict, one, that they're searching, and two, what they're searching for. We use this as a kind of a human-robot interaction thing so that robots could make decisions about what to do to complement the behavior of the human. And so typically it would run them in a generative mode and say, you went here and here, I predict you're going there and there next. I'll go someplace else. That way I can guarantee that I will help and not hurt you in the performance of this task. We learned a search and track policy. Basically, the X's mean I don't know what the states are. It goes search track from left to right. You start by trying to run search in the null space of track so that if you see the event you're looking for, you will just supersede the behavior of the searcher. If you don't find it, you go to this little loop down here and you start sampling from those distributions, looking for things. By the way, if you find a feature that's highly correlated, you find a red blob of a certain shape, and you're searching for apples, that will change the posterior distributions of subsequent searching controllers. So the history of events actually refines those distributions so that you can get more and more specific as you start to accumulate evidence. I'm going to use this as a motor primitive now, and then we'll go forward to try to get to dexterity. We noticed this is also somewhat older work. I'm not going to let this video play because it takes too long. What I really want to point out in the course of this example is this graph over here represents a very idiosyncratic relationship between that robot and that big pink ball. The 11 bits that you see inside these nodes are control status returns that are all kinesthetic in nature. They don't have any of the visual features. We strip them out because it gets too complicated otherwise. This is also a segment of this graphical structure that requires that at least one stable grasp occurs at all times. And so this is kind of a manipulation graph. It's all kinesthetic. I will never drop the object. And anything I can do in terms of manipulations is mapped onto here somehow. The arcs you see between nodes are one of the 11 controllers running. And it transitions the system, sometimes in a very coupled way, into a new kind of state feedback vector. If things don't unfold the way you anticipated, then you can stop and take contingencies as a result. Now what it's doing is manipulating. It just ran one grasp in the null space of another grasp, and then when it got there, two stable grasps existed, and it could discard one. And there I went and let it run the whole way through, so I hope I don't run into time problems. The graph is very powerful, but it doesn't scale too well, so we looked at using dynamic Bayes nets, where we have a distribution over objects we know about in the top, over aspects of those objects. That is, if we expect to be able to see instantaneously right now from this perspective, or touch, or hear, right? All represented as these kind of search track associated features that we get feedback from, aspects, and down below the constituent features that we might be able to track. We select an action, it transforms us into a new posterior distribution over all three kinds of events. All right. Now I'm going to skip right through this stuff. Hopefully you have heard of POM-DPs before, and some of you are probably better at it than I am. But you can represent this as an impartially observable system, very important for dexterity, very important for real robust robots in the first place. This is just how it maps from states to actions to observations to state transitions to observation probabilities and essentially and eventually to an external reward. And so you can learn policies in this space. I think this one was supposed to be hidden. Let me try it anyway. Here is a robot trying to build such a model. Nope, it won't run. Okay, I'll skip that. You can represent many, many interesting kinds of tasks. We propose maybe all the tasks you really need in terms of a desire to condense belief over those three levels of distribution. Either you want to know what object it is from a set of objects, or you want to know if you can find a handle which might be a particular aspect of many objects, or you might just want something read, in which case you could be down at the bottom level and you can interpret the history of evidence you get in order to figure out if you can find that target. That target could be an assembly that has a certain spatial constellation of features in some particular spatial arrangement that satisfies the task. And we've done a little bit of experimentation on that. To update the posteriors, we just run the DBN. So this is like a common filter for those of you who understand common filters better than DBNs. It just takes a forward model. In this case, it's the model of those objects we have. Takes an action, projects it to a new expected state, and then it fuses the new observations into the new expected state, just like a common filter. All right? Constantly reevaluates the information and updates all the distribution about. And then a simple planner can just watch the posteriors on those distributions I was talking about in the search. And it can say, if they continue to change, I'm interested in exploring that, and the planner that will select the action that makes the distributions, reduces their entropy the most. That is, makes the predictions more and more deterministic. All right, so what does that mean? That was a lot of abstract stuff. One example before I close. This is an example we did recently. That's a U-bot. We use a U-bot. It's a 12 degree of freedom balancing robot that's only about this high. It is chimp in configuration in that it has a large reachable workspace on the floor. And what you'll see here is that this is a particular kind of object we do for testing. It's marked with distinctive markings on each face, but there are 6 faces and you can't see them all at the same time. The goal of the robot is to find out if this object belongs to a subset that is a goal, and to put it over on that side if it is, and put it on this side if it's not. We've done some pretty significant statistical testing of the response of the system. We get response rates up in the 98th percentile. Oops. I hope this one runs. Yeah, it will. Okay, so what you're seeing, this is sped up a little twice, I think, is the distribution of belief over here on the x-coordinate is all the object knows about, and in this case it knows about 100. This is a POM-DP, so we were worried about scaling. We've done 1,000 and 10,000. I'll show you some results in a second. You see this initially rather uniform distribution over that set of 100. As a result of each kind of inspection of the object, which could involve touching it, because touching it and moving it changes what you see. And so that could be highly predictive towards a dramatic future reduction in entropy. The planner can find those quite easily. You can see the belief start to condense over here, and in just another second or two, it will condense all the way to a single object, which is the task, and it will then deliver it. I'll let it condense belief one more time before I move on. It does it by executing an action, the consequences of which are likely to be informative. The most informative of all the actions it considers. Maybe it's going to do it. Oh, there it goes. Okay, so I'll spare you the the pick and place and the grasping, and then takes it over to that spot. We'll move on. Like I said, POM-DPs are notorious for scaling badly. So we looked at it 100, 1,000, and 10,000, and most of this was in simulation because our robot, you saw how fast it moves. You can see it's a dramatic reduction in uncertainty in the system with additional actions, and you can't really see the difference over here. It just goes to 5.2 from 3.3 over 2 orders of magnitude increase in the number of models it has in its head. This is very good news for us, and so we were a little excited about this. We're thinking about what to do next with this idea. We would like to study information-driven tactile exploratory procedures, so it might be possible that the same kind of belief optimization framework will lead to plans for interacting with your tactile sensors with objects that might be highly informative, and coupling them to motor commands, for instance, to get texture by moving and things like that. And that's ongoing work in our lab. We'd like to think about belief networks as a explanation or an experimental model of the neocortex. We'd like to balance cost to get an information gain. Right now, we don't care how long it takes you to compute something or how long the action might actually take, how much energy it will consume out of your battery. All of that should be considered as well. And for those of you who know about the SLAM technologies, SLAM is simultaneous localization and mapping, which is very similar in its nature to this kind of a technique. But we would like to generalize that to simultaneous problem solving and modeling, SPAM, yes. We think that you will be able to solve general purpose problems that have to do with condensing belief over descriptions of the environment you'd like to have the environment conform to by doing the same kinds of greedy actions. And maybe we don't need to be greedy. Okay, so I'll conclude there.
So in your talk, you showed different kind of tasks and which were controlled with a dynamic model, and the dynamic model had got different modules which were interconnected. My question is, how do you decide on the interconnections and the number of these dynamic primitives that you use based on the task? So if you change the task, how much human needs to look at the task to divide it into these sub-dynamics? Or is it purely model-driven?
We learn our models by direct exploration, by direct interaction with the object. So it played with that thing, and it tried random actions subject to the, if the action you were going to select threatened to destructively interfere with the constraint, which was to keep a grasp, it wasn't allowed. So it tried all the other actions. And then it just remembered what transition state caused. That is how they were coupled to other things. So they built them that way, and we've been building models at the same time that we use them for tasks, which is the interesting, that's why it's related to SLAM. However, there are only 11 bits in there. There are more in the full representation of that interaction with that object. We only used 11. You could use 30. You could use 5. We selected them. So it's related to some work we're doing on developmental programming for robots. And the stages of development impoverish the state representation and then slowly relax it so that you can get more and more expert kind of representations. So normally that would be maturation and growth that does that in the cortex. We do it for our robots. And eventually, after it builds models, we decide whether they're good enough. If they're not, we try to substitute things and let them build more, and we go from there. Good. It's lunchtime.
I'd like to finish up and thank all the authors for all the presenters. We are back. Okay, so if people could try and have them, 45 minutes. don't know if I start back again. Put back on time.
they're online, I think.
Okay. Oh?
Yeah.
Do you have videos with audio, Professor?
Yeah, no audio. Hi. Bin online. Ja.
Okay, good afternoon to everybody. I'm Nikos Sakarakis from IT. I'm pleased to be here in this fourth series of Jam Session on Robotic Research, which is getting more and more attention every year. So I will introduce the first three talks of in the afternoon, and go very fast to the first, which will is titled Biologically Inspired Periodic Motion Control, and will be presented by Alin Abdussafer from Robotics and Mechatronics at DLR Germany.
Okay, thank you, Nikos. Good afternoon, everybody. I will try to catch your attention after lunch with a talk which is in some sense related to TAG, but actually in a very wide sense, in the sense that, as you will see, we have also some ideas of synergy, but now applied to locomotion mainly, also a little bit to manipulation. But first of all, I will just give you a short link to the presentation which will be given by Thomas and the colleagues in the TAG workshop. And our contributions were, first of all, exploiting the synergy ideas for architectures and algorithms for controlling artificial hands, studying human hands kinematics in order to study synergies and also apply it to design of robotic hands. We had an integration of a tactile skin, which we will hopefully see in the demo tomorrow. And we developed several design paradigms for robotic hands. But again, this will be presented in the workshop tomorrow for the work package 6, and in the work package 8, again, work from our bionics group. We have here mainly, the work on one side of Claudio Castellini, who used EMG measurement in order to teleoperate robotic hands, and also force and independent position control of the hand. And on the other hand, we have Jörn Vogel, who did the same for the arm. And tomorrow, I think it's a very, very new result, actually, showing the integration of the two. For some reasons, check. So here we have, I think it's a quite interesting result, because we can use EMG to both control the fingers and the arm position independently. So a lot of degrees of freedom. The hand itself has 13 degrees of freedom, 7 degrees of freedom in the arm, and you can command both positions, gestures, but also forces. And we are using this technology for giving paraplegic people a possibility to command robot hands, or otherwise impaired people. But this is just the link to tomorrow's presentation. What I would like to talk about is actually about cyclic motion, and cyclic motion for systems which can be very, very difficult to model, as for swimming, crawling, running. Actually, I could not find a video from the people working for the cup yesterday afternoon. I was quickly looking in the 5 minutes for something with World Championship, but I think they were running for the cup faster even than Bolt. Anyway, of course, the robots we are trying to use are the variable compliance robots we developed in many European projects and many other projects at DLR. And the idea is to use the compliance of the musculoskeletal system to duplicate it in a technical system in order to be able to store energy and to be much more efficient in cyclic tasks in terms of velocity and power. And there are some larger theoretical questions related to this. So we are talking about cyclic motions, but as you see, this is not a simple cyclic motion, but of course it's periodical, but it's a highly nonlinear system. So at the beginning, when we started talking about it, was not even clear under which conditions will you have periodic motion for, you know, the rigid body connected by elastic elements, highly nonlinear elastic elements, highly nonlinear rigid body dynamics. So we started with some very simple experiments and observations, and just to compare it to the state of the art in this area are the central pattern generation concepts, and Icebird is one of the most well-known persons using this in robotics in order to command salamanders and so on. And the idea there is that you have neural oscillators which are in the spine due to feedback loop interconnection of neurons. Some oscillations will emerge, and these are mapped through some nonlinear mapping and commanded in a more or less feed-forward manner to the body. As a control person, I'm very suspicious when people are talking about open loop, because, you know, the body might change. If you have just a small phase shift, the body will get out of phase. So I thought, well, there should be some strong feedback loop in this idea. And on the other side, this central pattern generation usually do not address elasticity of the body. They work with rigid body dynamics, and elasticity plays a minor role there. There have been some attempts of introducing elasticity, but mainly it's a feed-forward approach for rigid body design. What our goal is to find simple and robust control that exploits the intrinsic dynamics of the robotics, elastic robotic system, or of biological systems. And as I mentioned, the question whether you have cyclic motion, cyclic periodic motions intrinsically in a body is a difficult one for nonlinear systems. And as we know, even a very simple two-joint system is a chaotic system by itself, right? So you will never get periodic motions by just starting from any initial condition for such complex systems. On the other side, you have simple observations if you are asking people to, you know, take a element of several links connected by springs and ask the human just excite that, he will succeed this within seconds, which is somehow amazing. We played with kind of small gimmicks and asked people to do so, and I mean, it's a trivial task for humans. And on the other side, we had the work we've done. I mean, we had a PhD. There was today in Pisa. It was the work with Sami Haddad at DLR, some strong collaboration with Pisa, where we applied optimal control technologies to exploit elasticity. And what turns out, I mean, this is a demonstration where the robot stores energy in the springs and throws the ball. But what turns out is that usually you have to train the system to solve the optimal control problem for hours, while again, for a human, it's a trivial task. So the question was, is there maybe a better approach, an easier approach to tackle this kind of optimality problems? And that's how, because we missed any theoretical framework at the beginning, we just started by looking at the humans and doing some simple experiments the human has a force feedback device and gets a simulation of a limb or a leg, arm, whatever, and you can change the parameters, the inertia, the stiffness, and the elasticity of the system, and the task is the same. You ask the human, could you please bring the system into oscillation? And of course, the human succeeds to do that, but as we have seen, he does not always succeed. So there are indeed some particular properties of the system which help making the problem a simple problem. And as you see here, it's a highly nonlinear oscillation. You see this is anything else but elliptic motion in the space. And if you are asking the people what they are doing while they are succeeding to do so, they will amazingly respond all more or less the same thing as saying, you know, I observe the force, so it's a force feedback device. You can feel the force applied by a robot on your hand. And what they are saying, I'm observing the force and I'm waiting until a threshold is reached, and if the threshold is high enough, I just push hard, which is exactly the way you would excite this swing. Of course, it's a nonlinear dynamics, and if you would even take the dynamics of the rod, it's a complex system. But what people are just doing is waiting at some point and inputting some energy with some accurate phase into the system, and then let the system evolve according to its natural dynamics, instead of going there and trying to, you know, to follow all the time the system and learn the whole oscillation dynamics. So this is a basic and simple idea. And when measuring what the humans were doing, the plots look like this. What you see is that indeed the red curve is the input from the human hand, and at a certain point he will indeed wait for a threshold in the torque, the black curve, and then push hard. And of course you don't have discontinuities in the human motion, but by abstracting this, we came up more or less with this model, also by the intuitive description, saying I'm looking at the torque in one direction. If it's bigger than some epsilon, just put a delta on the input. This might be position or might be force. When we came out with this idea, I had some discussions with colleagues, also with Christian Ott, and of course he asked, well, you observed that for the human, but is there any other reason for taking this low? It could be any other. And indeed, we spent some time asking ourselves, what's the reason? And the first answer was that indeed, for the 1 degree of freedom, you can show theoretically that this kind of bang-bang controller is indeed the answer to the question, reach velocity in minimum time. So then you end up always with bang-bang solutions. So it might be an optimal solution to that task indeed, minimizing velocity, energy, and so forth. But what is less seen in this, but you will see later on that it will match more and more this idea, is a kind of 1DOF neuron. Just wait a few slides and you will recognize it. And this seemed to me very exciting. Now coming back to the question, is it that easy to excite anybody? Obviously not. And if you have just springs and inertias, then you have most of the time chaotic systems. So there are no periodic motions, and you will have a hard time doing, you know, model-based control in order to impose periodic motions. While if you just add a little bit of damping, then everything gets easy actually. What happens for this kind of serial kinematic structures is that the damping causes the system to have a first mode. If you have just a little bit of damping, so a psi of 0.2 or something like that, you have a first mode which is has very little damping, and all the higher modes are highly damped. So what happens basically is that the oscillation reduces to the first mode, and you don't really need to care in reality about the other modes because they will quickly decay. And we did identifications on our robotic system, and Dominic Lakatos did in his master thesis also some identification on human arm stiffness. And if you look at the human arm stiffness and damping properties, you will find out that amazingly they have exactly this property, that the plant is easy to excite. You have one mode which is not damped and you can excite it, and all the other modes are well damped, so just don't care about. And in the experiments, it's really turned out that a human cannot deal with those systems which do not have damping. So when we did these experiments with a force feedback, indeed, if you have, you know, for one mode relatively high damping and for the other low damping, this human is very good in keeping this oscillation motions, while as soon as you have something like that without damping, so taking the damping away, the human fails to excite it. So maybe on one side, maybe we are good in controlling bodies, but on the other side, the body is designed such that the task is just simple. This was the main conclusion. This is just a transactions paper which was published online this month, comparing the experiments for humans and robots. Okay, and of course, comparing to a linear system in one dimension, you notice that it's not linear, but it's highly nonlinear. Well, the controller itself, what does it do? We did a lot of stability analysis to understand what is the method of stabilization. And what you see here, green is the motor side, and you have the spring and the link side, and you just observe the torque, and at some threshold you fire. And what you can show is that by this procedure, you basically always inject a constant amount of energy into the system. And of course, because the dissipation continuously increases with velocity, you will find an amplitude of the motion which is a periodic orbit, because you know, it's different than the van der Pol oscillator, where you have once negative and once positive damping, and that's the process of stabilization. In our case, you always have positive input of energy, but because dissipation is continuously growing, so also the stability depends on this damping property, you will have a limit cycle which is stable and attractive. Well, actually, I have to switch. Sorry. I wanted to show this. I just included the slides from Antonio 1 minute ago, and I included them at the wrong position. But this is something, Cecile, I think you remember from the Safari review meeting. So because we presented this on the Safari review, and we discussed this with Antonio, and then in the afternoon, just in half an hour, the colleagues implemented them. So DLR and Pisa colleagues implemented that on the VSA cube. And we have shown it's just a few lines of code, and indeed you get limit cycles, you can change stiffness, you can change equilibrium point. It just works without any model knowledge, with a high nonlinearity, so it works perfectly in one dimension. And as I told you, in just a few seconds. The question is, so the convergence basically is instantaneous, and the implementation was also very quick. Now the question arises how to do it. We have seen it works for 1 degree of freedom, and the experiments were 1 DOF, how to generalize to many degrees of freedom. And we would like to keep this idea of observing some torque, looking at the threshold, and then firing. But in order to do so for the whole body, you would like to reduce the analysis of the whole motion of the many degrees of freedom to just 1 degree of freedom, right? So you do a change of coordinates from one large manifold to just a one-dimensional manifold, and then apply the same control concept there. So what's the reduced manifold? What's the 1 degree of freedom on which we could reduce the analysis? Sorry, something has been mixed up on the slide. So let's go on this slide here. And the idea is the following. Remember the example with the swing. Now you will have this black trajectory of the system oscillating somehow. And you would wait at a certain point just for the system, so not following the whole trajectory, just waiting at a point and analyzing the nonlinear system just at that point. And at the beginning, you would give an excitation in a wrong direction probably, then observe the system, how it oscillates, how it comes back. Then the next time you will correct the direction and correct an inner during a few iterations, you will converge to the ideal excitation in that point, which maximizes the energy input, basically. And this is the direction which is tangent to the first mode. And now looking to what happens, I mean, if you derive the mathematics for that, it turns out that what we are doing a coordinate transformation from the measured torque tau in the joints. We are doing a linear transformation to a tau z, which is one-dimensional. And then in this one dimension, we are applying the same control law of observing the threshold and then firing. And then from this one dimension, delta theta, you generate again backwards the inputs for all the torques. So that's the idea. Go to one manifold which corresponds to the first mode, do then the firing, and then transform it back. And now looking to what happens, then this looks like the picture above. So we are measuring all the torques, then applying some weights which are adapted continuously. And then if you reach a certain threshold, just fire. And this is indeed a very simple model of a neuron. And putting everything together, what we are doing is we are looking at the torques, going to one-dimension firing. Actually, this is not just a step, so it's a hysteresis system. So you need 2 neurons in the hidden layer, and then transform back to the output and command the positions to the system. So that's it. The only thing you have to adapt are the weights, which are adapted, for example, due to a simple Hebbian rule, and the threshold on which you fire, which is also a weight from neural perspective, and that's it. And now coming back to my video, sorry for that, for messing up the order of the slides. But what happened here is that, indeed, we used exactly this concept, and then Dominic is coming and giving some initial impulse, and then the system starts to oscillate, and you see this bang-bang behavior. And you would wonder, you see it's a perfectly periodic motion, which is amazing, actually, for the fact that you have a complex nonlinear system. And it's even very repeatable. And this is a video I also inserted 2 minutes ago. I haven't even seen it. I just trusted Thomas that is doing exactly what it should. We did it at Automatica, and we are using this cyclic motion, even in contact, to carve a DLR sign on a card. And you will see by using some iterative learning, you really can card also with high precision, actually, with accuracy of less than 1 millimeter, with this periodic task. So you can do really some very precise tasks, exactly only with this model-free controlling of the cyclic task. Okay. And what's the connection to TAG? So if you want, you are controlling in one synergy space. You are taking the very first synergy, you are transforming all the sensory inputs to one dimension, then do some actions there and transform back. So this is actually fully in line to TAG, although not purely emerging out of TAG, but having strong relation with it. So is it biologically plausible? Actually, if you look to the way we are adapting the weights, pure Hebbian learning is doing exactly what we would like to have. So Hebbian learning with the so-called OJAS rule, with some normalization of the weights, will lead exactly to the control we would like to have. What we are still missing is a copying of neurons. And neuroscience people say they don't believe there is something like weight copying. While Dario Floriano just sent me some papers where they presented such strategies. So it's still kind of open. You can, indeed, there's no weight copying directly neurons, but you can imagine mechanisms such that identical weights emerge in 2 different areas by presenting the correct type of inputs to the layer. So still, I hope that is biologically plausible. And what happens then if you are, these are some simulations for running. It's even more interesting for running than for the manipulation, to be honest. And this is the model for different configurations the same. You have the body, you have the elastic legs, and sorry, I will just go ahead. And then this running behavior just emerges from the body configuration and this very simple controller. And you see it's pretty robust also to perturbations, to uncertainties, and so on. But then if you turn the joints in a different configuration, instead of the crab motion, suddenly you will have kind of a jumping, I don't know, deer motion or whatever. And if you just shift a little bit the center of mass, then you will have some kind of galloping, with exactly just the same controller. And what the motion which emerges is the intrinsic behavior of the body itself, is the resonant mode of the physical body, which is, I think, kind of interesting. And well, still we don't have a hardware to play around, but I just checked with my kids, and even a simple Lego system will start to jump in a certain way. So in conclusion, the bang-bang controller is very simple and robust, and you can excite oscillations of an elastic body, robot or biological, without any prior knowledge. And the controller can be implemented in principle by a few neurons for a whole elastic body, at least in principle. Probably it's not so robust for a biologist. And it leads presumably to motion close to optimal performance, which is kind of interesting, because among other many properties of neurons, you could even say that, you know, a neuron is also an answer to the question of optimally exciting energy-efficient locomotion for elastic bodies, which is interesting. And of course, my question to biologists, might be this a plausible hypothesis to generate cyclic motions in biological systems as alternative or in going together with the central pattern generations, and is it worth verifying it experimentally? This is a question I would have to you and maybe also to Mitsuo, and can be even used to control biological systems, for example, paralyzed lips and so on, because we don't need any model. Is my time over? Okay, I would have 1 or 2 slides more if we have the time, just to show that we have another. So this is completely model-free, and I would like to compare it. Of course, if you have a perfect model of the robot, you could do it the way we are doing it usually with complex nonlinear modeling and so on. And then you can do a stabilization of the limit cycle by doing a bit more control and trying to shape the nonlinear modes. And then indeed you could excite also higher modes. So this is just a video I wanted to show that having a perfect model, you can excite not only the first mode of the system. You see here on the picture, blue, green, red, and yellow are the first 4 modes. And this is the first mode in this configuration. More interesting at this point. Let me check. It's of course robust to perturbation, so you can restart and it will always emerge to the limit cycle. But this is another configuration. This is the first mode. You see it will move this way to the side, while the other modes are almost completely damped out. And if you go to some other, I mean, you can the same way excite the second mode only and keep the other modes damped well. So comparing the two methods, you have for the model-based control, of course, if you have a desired dynamics, then or a good model dynamics, then you can, of course, largely change by control the dynamics of the system and let the system behave like something very different. But it costs energy, and you need high derivatives. That's a problem which you have with elastic systems. While stability analysis is also is always very easy when you have good models. While for the model-free control, it's robust against parameter uncertainties. It uses only measurements of the states, no high derivatives. It's potentially more efficient because you are interacting with the system just to a very little amount. But of course, it requires that the physical body is such that it runs by itself, more or less. So the plant dynamics has to fit to the task. Okay, this brings me to the end of my presentation. Thank you very much.
So, are there any questions? Yes, please.
This reminds me. This reminds me a little bit about Rodney Brooks' ideas. I wonder if you could give some kind of comparison.
I'm not sure. I don't think I'm aware of Rodney Brooks' ideas in this direction. I couldn't give you now a comparison, but maybe we should talk.
Yeah, because he also had the idea of this reactive operation, that you don't have a feedback loop, you don't have a model, but the motion is actually controlled by the feedback from the environment.
Oh, okay, that's a point. So maybe it's more related to the work from the leg lab at MIT, which they have similar reactions. So we discovered thereafter that maybe there are even stronger relations to what they are doing, to big dog and so on.
So very exciting, and you use a lot neuron for your control law to have the maximum output when input reaches some threshold.
Yes.
But actually, in some lower animals like nematode, C. elegans, or invertebrate animals, some neurons are not like that kind of a threshold element, and they just generate graded potentials.
So it might be interesting to see the differences of cyclic movements between real neuron animals and versus graded firing neuron animals.
I see. So actually, of course, we are far from being neuroscientists. No, not at all. I had some tangential to computational neural networks sometimes. So my hope is actually that by giving this presentation, I would, excite some neuroscientists about this topic and get some feedback, whether this is plausible. Do you know something similar? I mean, I would like to get in interaction with you or other neuroscience people to understand whether it makes sense to make this hypothesis in biological environments. What we know by now is that it works well for robots, that's for sure, and is very efficient. But whether we can make a point for biology or not, we are just at the beginning of the road. Thank you.
Maybe one last question. Okay, then we move to the next presentation.
Thank you.
So the next talk is actually on the area of grasping. So the full title is Grasping, Regrasping, and Not Grasping. And will be given by information that comes from CMU, Pittsburgh, US.
Hello. Thank you very much. It's a thrill to be here. Some of the work relates to work that's been going on in this university for many years. So, I'm excited to see what you all think of it. Even if you have critical comments that are too intense for public display, email me. And anyway, there are a lot of people involved in this and some sponsors, but I'm not going to take time to go through them now. So this work kind of started with thinking about grasp taxonomies, and I know a lot of people here are familiar with them and maybe have been involved in creating them. This is the Kotkovsky and Wright taxonomy from 1986, so it's been around a long time, and it's a lot of us use it one way or another. You have power grasps on the right, which could be like an enveloping grasp. And precision grasps, that's on the left, and precision grasps on the right, and then they're further broken down from there. And so the relations among these are, subtypes and subtypes, but there's nothing in here about how to get around in that. So these are different grasp types. The question is, how do you navigate the grasp taxonomy? How do you switch from one grasp to another? Here's an example. So this is from 1971. Richard Paul's PhD thesis was about this system that could move blocks around. And if you're watching, you notice it picked up the block, and then it put it down, and then it grasped it again before it moved it. And the reason you have to do that is that sometimes, if it's like that, and I want it to be like that, okay, how am I going to do that? Because I want to grasp it like this, but then when I put it down, my hand's in the way, right? And so when you go to grasp it, you need to think not just about the obstacle that's here now, but also think about where the table's going to be object and choose a grasp that's appropriate. And in this case, I can do it, but sometimes you can't, okay? And sometimes, in fact, it would have to re-grasp a block twice in order to do the necessary motion. So this is pretty common. It's well known. You can ask the question, well, what do humans do? And the answer is, as usual, humans do all kinds of things. This one is kind of interesting, I think. Essentially, it is a drop. I say she's dropping the phone, but she's not dropping it all the way to the ground. She's dropping it from a pose like that to a pose like that. So it's just, she's defining a single degree of freedom by the way that she's grasping the phone and then letting gravity take it down. And of course it's, well, hey, we do it with our cell phone, so it must be safe, right? Sorry? No, that's not a product placement thing. I'm an iPhone guy, so that was a student project. So if this is dropping, then I guess this is throwing, okay? It's you're using the momentum because gravity is pointing the wrong way. Here is an interesting sequence. It's funny, we're so used to doing this and so used to seeing it that it's really hard to sort of force yourself to look at it analytically and look at it bit by bit and understand what's going on. But let's just try it for a second here. So if I back this up a bit, what goes on from there to there? What about that bit right there, just right there? The phone is still sort of hanging down. It looks like she's got it between her thumb and her forefinger and letting gravity stabilize it while her hand is rotating about the pivot and then putting those 3 fingers underneath, the additional 3 fingers. And at that point, she's got what looks like a statically stable grasp, or an equilibrium grasp because she knows where gravity is. And at this point, she has looked at it, she's realized it's upside down. Well, okay, this just goes on and on. You can spend all day trying to figure out what's going on with this one demo. So the question is, what are the different ways to change grasps? And now in this case, of course, she's got a really sophisticated hand. But you know, in the first example, we were looking at that Stanford manipulator that had a really simple hand. And you don't imagine that a simple hand is capable of the kind of reorientation in the hand that a human hand can do. But we're going to go back and look at that. So here's a video we recently shot.
We're looking at regrasp actions. Actions that change the pose of the object in the hand. Here at the Manipulation Lab at Carnegie Mellon University, we are exploring regrasp actions for simple grippers, like the MLab hand shown here, which uses only one actuator. So far, we have developed 12 regrasps, which we have grouped into 3 categories. To bring such dexterity to robot hands, we must look around the hand and look at the entire hand-robot environment system. Grime. Some of these actions don't look like regrasps, nor could they be described as in-hand manipulation, but all of these are ways to change the pose of the object relative to the hand. Some of these actions are also useful when grasping or placing an object. As you can see, none of these regrasps in sequence. A few of our dynamic regrasps, which transfer the object from an enveloping grasp to a fingertip grasp and back again, were shown to run in sequence 50 times in a row during our experiments. In the future, we hope to model these regrasps and use those models to plan new sequences of regrasps. This will give robots the capability of arbitrarily changing the pose of the object in their hand.
So that's the idea. This isn't a grasp taxonomy, but the nodes of this grasp look kind of like the nodes of a grasp taxonomy, but in this case, the arcs indicate different motions that we would like to make. So actually, this looks very similar to the graph that Rod put up earlier, which was called an aspect transition graph, attributed to Rob Platt. Is that right? So we weren't sure what to call this. When did Rob do that? 96. You think everybody's forgotten? We can get credit for giving it a new name, and or should we go back and cite him, do you think? Anyway, so I guess this is an aspect transition graph. But you know, when you start doing this, and you know, pretty soon you realize there's nothing specific to grasps about this. I mean, some of the grasps involve putting it down and picking it back up in a different way, which is sort of the conventional regrasp. And as long as you're doing that, well, you get pick motions and place motions. Anyway, that's the manipulation graph. The dotted lines are ones we've just imagined that we'll implement someday. The solid arcs are implemented, and so a lot of those paths that you can find, as long as you stick to the solid arcs, we tested. This is a similar graph for the cylinder, for the cylindrical block that we did. And we just ran through several of the grasps and tried to figure out sort of how do you characterize them, what distinguishes one from another. So some of these are sort of just kinematic or quasi-static, relatively straightforward. Pushing in fingers, so you just run the object into an obstacle and let the obstacle push it relative to the fingers. You can do that for a fingertip grasp or an enveloping grasp, so that's A and B. You can roll something on the ground prior to grasping it. This drooping in fingers action is kind of interesting. So, you know, if you wanted to pick something like this up, you could pick it up like that, sort of like her when she took the phone out of her pocket. It looks very, at least in the video, it looks kind of not very robust, but that was one of the actions that worked, I think, 50 times in a row. Then there's another class, sort of what we're calling passive dynamic actions. The dynamics is important, but we're using gravity to provide the energy. So just dropping something, but as it rolls out of the fingers, you can get some action that way, or letting something roll down the fingers to the palm, or letting it roll away from the palm out to the fingertips. And then the more exciting ones are where you're actually using the dynamics of the arm. So throwing from the palm to the fingertips or the other direction. And then, you know, C, you can imagine, we just discovered that by accident. It started as a bug. Sometimes when we were throwing to the fingertips, the block would rotate in the air. And we said, oh, well, you know, sometimes that would be a good idea. So let's give that a label and claim we have a feature rather than a bug. So we did a lot of experiments. Basically, the way this worked was the grad student, Nikhil Shavandapal, who was mainly responsible for this, he would work all day and get the thing tuned up as well as he could. And he was very disciplined about this. He would do the best job he could getting it tuned up, and then he would run 50 trials in a row. Okay? And what I'm telling you is he didn't run 5 trials in a row and, oh, it didn't work, I'll fiddle with it some more, and now I'll try again. You know, and you keep doing that until you get 50. He was much more disciplined about it than that. You know, but still, the important thing is these are handcrafted. You know, they're point solutions. So for this block, on this day, you know, tune the code up, getting it running as best you can, and then run the trial. So there's a lot of work to be done. So let me just sort of back up a bit and talk about the whole line of thinking that got us here and why we think it's interesting. So we started out impressed with how important regrasps are, and let me just say a little bit more about that. So, I mean, it has been known for a long time. I showed you a Lou Paul videotape of it. Actually, if you go back and read the papers being written by people in the 50s on teleoperated manipulation of nuclear material, you will read there exactly the same thing that I just went through, this explanation of why regrasps are important. So this is one of those things that's been known even before the roboticists got involved. So we're looking at what are the different ways that one can change grasps. Now, the thing I haven't discussed is the way that people usually talk about it in our community, which is what we call sometimes dexterous manipulation, or sometimes called in-hand manipulation. And that's the idea that you have 3 fingertip contacts, and by controlling those points, you can rotate the object in the hand. And if you want to do this in the sort of most straightforward way that Ken Salisbury invented in '82, you need at least 9 motors, right? So the idea was whether you can get motion in the hand to happen with a simple hand, not 9 motors, and this one. Okay, so in the videotape, that hand was using only 1 motor. And the answer is, well, you do it because you're using other things, right? You have, in our case, an industrial robot that has 6 degrees of freedom. It's got 6 motors, and we're going to use all of those to make up for the lack of complexity in the hand. And we're using other resources as well, right? We're using gravity, using the momentum of the object, and sometimes we're using physical contact with the world. So trying to think about how to compare these two ideas. If you think about the idea that I'm going to rotate the object just using the resources of the hand, in the biological literature, sometimes you see the phrase intrinsic manipulation, intrinsic motions of the hand. And so we're thinking, okay, well, that ought to be called intrinsic dexterous manipulation. And we could call this other idea extrinsic dexterous manipulation. So it's basically ideas that have been around for a while, but perhaps a new perspective. And it turns out, as I noted before, it's not just regrasps. It seems to be all of manipulation. I'll just mention one other old reference to this, which is one of the more kind of undercited papers I think that's relevant to this, which is that if you go back and read Ken Salisbury's original whole arm manipulation paper, you know, everybody now is impressed with the whole arm manipulator, the WAM manipulator. But the original paper wasn't about the arm so much, it was about the idea that from a kinematic perspective and from a mechanics perspective, there's not that much difference between this body, you know, which we call a phalanx of the hand, and this body, you know, which we call the ground. But if you're doing something like that, okay, you've got a whole chain of mechanism here between this body and this body, which isn't necessarily so different from the chain that connects these two bodies. So the WAM idea, the whole arm manipulation idea, is the idea that ties together all of these different regrasps in a sort of unified framework. Anyway, this is just a work in progress. So far, we've got these point solutions I talked about. We have in mind, you know, we have a perspective that's pretty similar to Rod's. We believe there's a lot of behaviors out there. We need both analytical modeling and empirical sort of statistical modeling. So we've got a nice framework that we plan to apply to this. We are working on an experimental system to gather data so that we can do the empirical modeling and go on from there. So that's it.
Are there any questions?
Just slightly. So one of the things I feel like you know, I wish we did more of was looking at tasks that don't involve prehension. A lot of times you hear people say that the hands are mostly for grasping. Perhaps it's true. I'm not sure. I've never seen it scientifically vindicated. When I think about things we do in helping people, you know, deformation seems to be much more a part of that, right? So I mean, certainly with self-grooming and, you know, but helping elder people and so forth. If you and then, you know, when you shake hands, you know, there you've got a kind of interesting duality. You know, it's not clear which is the hand and which is the environment. So maybe that's an example of what you're saying. But so I think the answer to your question is not much. No. Interesting.
Any other question? Okay, thank you very much.
I'm getting off easy.
So we move now to the next presentation that will be given by Marco Sandello from Arizona State University. And the title of the talk is Sensory Motor Learning and Transfer of Dexterous Manipulation.
Thank you. Okay, well, it's a pleasure to present my work here at this Robotics Jam Session, just before our final THU review. So I'm just going to give you a brief overview. If you can please ignore this, I'm just coming from the RSS meeting. I copied only the first slide. I promise the rest is new slides. It is about sensory model learning of dexterous manipulation. So we talked a little bit about what dexterous manipulation is, how you can define it. I'm going to tell you a little bit about the way we think about it. And so the work that we do in my lab looks at the way the brain controls the hand. And the reason why I like the hand as a model is that it embodies all the things that model control and neuroscience research case for. It's a complex system, complex from a perspective of motor machinery, complex from a perspective of sensory machinery. Just a great model to work with. But as I mentioned here, is also, besides being an intellectually interesting system to work with, it also has some very practical implications, especially for clinical and rehabilitation purposes. And I'm going to say a little bit about it. But these are some of the topics that interest us, and that is more lately we've been working with Antonio on the development of hand prosthetics using robotic hands. I'm also very interested in understanding the mechanisms of neural control of the hand, because that can also inspire optimizing protocols for rehabilitation of hand function. So the better you understand the mechanism, the better you should be at defining what really works in rehabilitating normal function. And also neuroplasticity. Professor Kawato talked a little bit about this as far as how the system adapts to practice and motor training. And so because the hand is so complex, we tackle the problem of neural control of the hand from several perspectives. We worked in the past on looking at single motor units, which is single cells, which is the smallest unit of control force, to looking at system level analysis, where we look at the way the brain may learn and store these representations of tasks. And I'm going to say a little bit about this later. Looking at the way you could track the hand, not just the hand per se, but also where the object is grasped, looking at feature, graspability of different objects. I'm going to tell you a little bit about something that we studied in the last couple of years, and this is non-invasive brain stimulation, which we also use as a system identification technique to better define the processes underlying learning and control of manipulation. Another project I'm going to tell you a little bit about is the use of virtual reality environment, which we are kind of forced to use because physical objects have limitations. Most of the physical objects we interact with are man-made, and we know gravity, and we know all of these properties. So it makes it really difficult to study how the brain adapts to using everyday tools. That's why we like to use also virtual reality environments. This is another line of research that we just started, and it kind of fits very nicely with what Etienne Bourdet was saying earlier about human-robot interactions. And this is a project with the IIT in Pisa with Professor Bicky also on the soft hand. So the topic I wanted to focus on today is anticipatory control, which is a recurrent theme in motor control, and it's basically one way in which the system can control movement without relying too much on reflex-based control. As we all know, reflexes are characterized by delays, and so the system learns to anticipate the consequences of our own action. And this has been from different ways since the early observation of this anticipatory control. And it's very ubiquitous. As you could see, researchers have defined this anticipatory control in a wide variety of tasks. But the one I'm interested in, I'm going to tell you today about, is anticipatory control grasping and manipulation. This is classic work by Johansen and Wessling from the late 80s. And what you're seeing is that it was one of the first that pioneered the systematic study of forces for grasping and manipulation. What's really interesting about this slide is the fact that the subject has been instructed to lift an object with different masses. And each of these traces indicates a different mass. And so this is the load force you apply to lift the object. This is the grip force you apply. And what's interesting here is that for each different mass, you see that these forces develop very differently. What's really interesting about it is that these forces develop differently before the object actually starts to accelerate. And this is considered evidence for the subject anticipating what the mass is going to be. And you could see even better here in the rate of force development, where you see this kind of bell-shaped like profile. So what we started to do, and this is taken from Johansson, we looked at this problem again, but looked at it from a different perspective. And we said, what happens if now you remove the constraint of contacts? And what I mean is, in this particular task, subjects are instructed to grasp the object at very specific points. And those points, in most cases, in research and grasping, has been dictated by where the sensors are. So we looked at this problem, but this time we said, why don't we make the contacts unconstrained, so that now you can grasp whatever you want on this particular surface with the thumb and index finger. And we use 6 degrees of freedom force and torque sensors on this side, and these are hidden from view by the subject. And to make the task a little more interesting and more challenging, what we did was to put a mass either on the left or the right of the object, so that when you lift the object, it undergoes a tilt. And what we asked the subject to do was to learn to anticipate the torque that you need to minimize the tilt or to prevent it. Not unlike what Johansson was doing by changing the mass, where he was asking subject to anticipate the actual mass and prepare the forces before the object accelerates. Now, why do we care? Well, we started to think about this problem of unconstrained grasping, and we reasoned that when you have fixed digit contacts, the system can actually build and leverage memory. In other words, if the contacts are fixed and you're always grasping at the same points, you can afford to use the same forces over and over and over. As long as you can recall them in an accurate way, you should be able to do the task accurately every time you grasp the object, as long as you can recall the forces that were successful earlier. The problem is that if you cannot, if you're not forced to grasp the object in the same points, every time you grasp the object, you have to recompute the solution for force that should change as a function of where the fingers end up on the object. And because in most cases, when I grasp a bottle, when I grasp an object like this, I don't always use the same context. They could change based on what I want to do with the object, could change based on noise in my planning or execution. And so this kind of shifts the problem a little bit from a purely memory-based control to memory integrated with sensory feedback of where the fingers are. And sensory feedback could also mean a lot of things. Could be feedback of my finger position, could be feedback of the forces I'm exerting, and ultimately feedbacks of more complex variables like the torque I want to exert. So this is the problem that the brain has to solve. So you have freedom to put your fingers wherever you want, which will change how you distribute the forces, both normal forces and load forces. But ultimately, the brain cares only about one thing, provided that the subject care about what you're telling them to do. So you're telling them, minimize the object roll, try to learn this best you can. And so the brain is to understand after the first or second trial that this torque has to be matched, but the subject is free to solve that problem in indeterminate number of ways. How do subjects do it? Well, what subjects do is from trial to trial, because there is variability in digit placement, they scale the forces according to where the fingers are. One thing I should mention, though, which is very important, that's why I underlined it here, is that this solution has to be made before the object actually moves. So you're using memory, but you're not using really memory of force because you're changing your solution all the time. What I'm plotting is the difference, is the distance, the vertical distance between the centers of pressure, which is dy right here, and the load force sharing. So it's the difference between this load force and this load force. And each data point is individual trials. So what subjects are doing, even after they learn the task, is that even though they exert the same torque over and over and over, the way they solve the problem is different every time they grasp the object. Then we thought, well, what happens if you change grip type? So even though these are normalized units, the variability could be less than a centimeter. So it's not that huge of a challenge. But then we said, what happens if I challenge the system even more? What happens if you learn the same task with 2 fingers, and after 10 trials, when you really learn the task, I'm asking you to change the problem over again, and now you have 3 fingers. Now, what happens is that the center of pressure that you learned is completely different. The force sharing is completely different. The only thing that stays the same is the compensatory torque that you're supposed to exert. And the question was, would you be able to do it or not? And sure enough, you learn the task with 3 digits. I'm asking you now to do it again, but with 2 digits, and there is absolutely no error. What this means is that subjects are actually using a high-level representation of the task, which is the torque, and it doesn't really care about the effectors. Now, what is remarkable about this behavior is that all of this happens within 300, 400 milliseconds between contact and the onset of the lift. So, and this made us think about potential ways in which the brain might work this out. But before I show you the theoretical framework, I want to show you another example where now we wanted to make the task even harder than just lifting an object straight. So this task is a torque task again. So we have the subjects using a thumb and an index finger. They place them on 2 phantoms. And the task consists of torquing this object, this box. And every time you exert a torque, you're going to move this particular cursor. And the task is to intercept a falling ball. They could fall either on this side or on this side. Regardless of the direction, the torque magnitude is the same. And we put some very strict constraints as far as time. We wanted to make this task very difficult. We wanted subject to actually learn it. And the trick that we play is that the box could be wide or narrow. What that means is that if the size or the width of the object is large, you need to exert lower forces to exert the same torque. And vice versa, if the object is narrow, you need to exert larger forces. So we're still playing the game of you need to learn the same task, the same torque. But now the question is, would you be able to scale the forces based on the width of the object? And the other trick that we played is that the width of the object could be either perceivable by vision. So you see the width of the object, and then you start squeezing. So you can predict what kind of forces go with that width. Or we eliminated vision after they learn the task, and then we just had the subject touch the object without seeing it. And the question there was, can I use non-predictive mechanisms, that is, just reactive mechanism using haptic feedback to scale the forces accordingly? So this is the way the task looks. And there is no sound, but you see, in that case, during the test A, which is with vision, you actually see the object, you generate the torque, and intercept the object. It takes, a fairly large number of trials, but subjects get it. Test B, it's a little more tricky because you don't see the width of the object. You just perceive with your fingers. So you need to recall the solution that you learned, but there is no one solution. There are 2, because one is for a wide object, one is for a narrow object. And what subjects do is that, surprisingly, they're able to do it even without viewing the size of the object. So by just feeling it, either a wide or a narrow object, they can exert the right effective force. The effective force is the force that generates the torque. The only thing that the system struggles with is the time that it takes to generate the same solution. So this is the time course from contact to producing that torque and intercept the object, which is here. As you could see, all you do is shift in this development of force later to the right, but you don't perturb the quality of performance. Now, we started to combine all these different data, and data I don't have the time to show, of 2, 3 other experiments, but we started to think about this and ways in which we could test this new theoretical framework for manipulation. And basically, everything seems to happen within this red box, and you could split the task in 3 components. One is a reach component, one is a force development, and one is the manipulation itself. Now, during the reach, you have a sense of where the fingers are in space because you can see them. So you could argue that you can predict where the fingers are going to land. You see them on the object. And that might give you a sense of how much force you need to exert. or how to distribute forces, okay? What happens is that often fingers might be occluded by the object, or there could be noisy information, both as the digits or the way a sense where the digits are in space. So what's really crucial here, and has also been proposed by others, is that contact is a critically important point in this particular process. Because now at contact, you can verify whether the fingers landed where you wanted them or not. But there is another important component here, that you need to transform the information about position in a way that allows you to scale the forces proportionally. So it's not enough to sense the fingertip position. You also need to do something with that data. And this is where this concept comes back again. So this high-level representation of the task is something you build by practicing, by learning the task, right? And so in the example I gave earlier, this is the torque. So you're now, in theory, ready to generate forces, but in fact, even as soon as you start squeezing the object, you still need to make sure that the forces you're exerting match the position of the fingers in a way that's going to give you the torque that you need to generate. And once this loop is over, you should be able to start the manipulation. So here, what's happening is that you need a sensing component of the position of the fingers, and you need a high-level representation of the task, which really doesn't care about what fingers you use. As I showed you earlier, it could be completely disconnected by what fingers you use to build that representation. And we think that this model is a general model of manipulation in general, not beyond the task of torque task or manipulating the object that we tested. Now this is, I think, the last slide. So in this theoretical framework, what we're proposing is that there is a much bigger role of sensory feedback of placement when you unconstrain the contacts, when you constrain them, than when you constrain them. This has to be proven, but we have some data that seems to be consistent with this idea. And what I'm showing you is wavelet transforms of the force rate occurring from contact to liftoff. So if you remember the data I showed you earlier by Johansson, when you saw those bell-shaped force rates, which are indicative of feed-forward control, if you feed a Mexican hat function, you see a couple of things in this data. Then when you constrain the contacts, first of all, these are 6 different trials for constrained and 6 trials for unconstrained. If you just look at this data, you see that the 6 trials are very similar to each other, which kind of confirms this idea that you can be stereotypical and more feed-forward when the contacts are always the same, right? What you see when you unconstrain the contacts is that each trial tends to be different, but you also see more high-frequency actually low-frequency responses here, which is basically these corrective responses that make the bell-shaped grip force rate look less bell-shaped, which is indicative of more corrective responses. So this is not a proof that you're using more feedback, but it's definitely consistent with that concept. This is the last slide, I promise. So all of this behavioral data is giving us quite a lot of thinking to do as far as what mechanisms might be responsible for these processes. And so this is what motivated us to start looking at transcranial magnetic stimulation. So this is a non-invasive brain stimulation that you could use to get different answers depending on the questions you want. In this example, we use single pulse TMS to probe the corticospinal excitability of the system. And what we found is basically we stimulate the brain at different points in time. In this case, we stimulate it at the time that I present you with a virtual object, with an image of a go signal. And after the go signal, you reach and grasp this object, and then we stimulate the brain here. And we tested the 2 tasks. One where you reach to grasp and just put the fingers here. And one when you reach to grasp and squeeze. So the kinematics is identical. What changes is the force you exert at the end. And what we found is that when you plan to generate forces, even though the kinematics is identical, you see a difference in both muscles. The level of excitability goes down when you are planning to exert force, which to us indicates that this particular system is sensitive to force planning even way before you start to reach the reach movement. This is a different experiment where now, instead of looking at corticospinal excitability, we're actually interfering with the system. So TMS can also be used to generate what is called the virtual lesion. So you transiently interfere with the processing of specific information. In this particular case, we managed to interfere with the variability of contacts on the object. And so when we do generate these virtual lesions, what you find is that the variability of contacts is increased, and so is the force rate development. And so this is work in progress. And just to give you an idea of how you could probe those particular questions in the model I presented earlier, but just looking at what particular brain areas might be involved in those particular processes. So this is my true last slide. So for the manipulation process, we're very interested in sensory model integration. So all of these processes that, by removing the constraint of contacts, opened up several new questions in the field. And so we'd like to understand a little better, mostly because unconstrained grasping is a way in which we normally interact with the world. And so I think there is value in understanding what kind of mechanism are at play here. And because also it might have a role in neurorehabilitation. And we're also interested in identifying the brain areas because non-invasive brain stimulation happens to be also used for neurorehabilitation. And so if we understand a little better what areas are involved, it's also likely we might be able to also target specific pattern of stimulation to areas that matter to these kind of tasks. And this is the lab and current collaborators. And of course, I'd like to acknowledge the funding agencies. Thank you.
Are there any questions? Yes, please.
Thanks, Marco. The picture you have where contact occurs, and then there's the red box, which is force development, and then there's manipulation. I don't know enough. I can't figure out how does one apply that in cases. I mean, if you're watching somebody doing something, it's amazing how quickly they proceed from one thing to another. So it doesn't. I don't know how this sort of idea phases fits in when there's a long sequence with no apparent gaps.
Absolutely. So one thing I should mention is that I'm looking at the precise, fingertip manipulation. So if you have a palmar contact, then the issue doesn't happen because you have much more stability, and you need to worry about this fine manipulation of force and position. So I'm looking at a specific case where precision matters, and you have to do something dexterous with the fingers. So usually what you see is that this particular time from contact to onset manipulation could take up to 400, 500 milliseconds. And this kind of analysis tells us that, in fact, there are quite big differences in the way these grip force rates develop from contact to onset manipulation. What's really interesting to us is that if you look at the behavior per se, whether you constrain the contacts or you don't, the quality of the manipulation is identical. But the way we're seeing this difference really happens at the level of how you get there. And it could, it's really, I don't have another slide where we show a Gaussian fit to the grip force rates, but the force development is actually very, very different. We're also finding difference here when we stimulate the brain, and even though we're looking at a few hundreds of milliseconds, it looks as if the way you affect constrained and unconstrained grasping is actually very different by stimulating a particular part of the brain. So we feel that I couldn't agree more that you're talking about a fairly short period of time. At the same time, this particular concept of effector independence is very similar to what Rod was alluding at earlier. That is that the brain has an ability of encoding these behaviors in an effector-independent fashion. And so it seems as if it's not that big of a challenge to recompute this particular variable if you want to use compute for the brain in a very seamless fashion. And it's what we do all the time. I mean, when I grasp an object, I'm not forced to grasp in the same points all the time to give it a given dynamics, right? But this happens, again, a few hundred milliseconds.
Any other question? Maybe I will ask one. So, where the replanning of the fingertip placement in this picture?
What is the plan for finger placement?
The replanning of the fingertip placement will go to in this picture.
So this will be right here. So during the reach, the idea is that you're driven by what you just did. There's a lot of literature showing that the latest experience with the motor behavior affects the way you're going to plan it. And so the idea is that during the reach, you're basically doing the best you can to redo what you did before because you passed. But as we know, sometimes there is noise in execution or recall of the memory. So one thing here is that at contact, you might be comparing the planned versus actual digit placement. And when so that kind of comparison is not really necessary when the contacts are constrained. Because other than visually guiding where the fingers go, you never have to question yourself whether the fingers are in the same spot or not, because you know that they are, and you see them, etc. But when it's unconstrained, you almost always have to verify that the plan of digit placement is being developed the way you wanted it. If it is, then you could recall the forces used before. But if it's not, we're arguing that in that particular case, you have to generate different forces. And to know what forces you need to exert, you need this kind of high-level representation to guide that.
Okay, thank you.
Thanks.
So this concludes the first session of the afternoon. We'll break for coffee. Thanks again the three speakers for the presentations.
I'm going to take this to Arizona. Thanks.
Jam Session. Next speaker is Mrs. Hayward. The title was supposed to be how the mechanics of electricity impact the tactile and gripping function of the hand. Vincent, that's so practice.
Yes, thank you. I have a microphone that seems to work. So I decided to change the title because it's because actually of Matt Mason, who is here. Matt invited me about 3 months ago at his lab to talk about what I was supposed to talk about now. So I decided to change because in Matt's lab, they recorded my talk. So now it's on YouTube. So now, and this one is going on YouTube, so I cannot do it twice. So I recycled another theme.
You are paid twice?
Right, which was done in London. It's more philosophical. It's about what it means to sense, and it's probably appropriate to the session here. Since the other speakers have shown very old movies, I felt entitled to show a very old movie also. Matt talked about Loophole earlier, who was doing manipulation in the 70s, and I actually was he was my supervisor, and so I had the same robot, and so that's my robot actually. When I was working with Loophole, that was in 81, and then the robot was the same one. It's a Stanford arm. And it was a very nice robot, like very light, very well built, very fast, and it didn't have force control. But actually, what happened in the lab is that it had force control in reality, as you can see in this video. The robot was perfectly capable of doing excellent compliant control. As you can see, it can slide on surfaces and follow surfaces. You could do impedance control very well. You could even put your finger in, it wouldn't hurt you. And it did all these things, and why actually, and then later in the lab, a Puma robot was brought in, and then from then on it was downhill, okay? Because the Puma was a really very different type of mechanical. This one had the force sensors in the joints, so you could actually survey out all the dynamics of the arm. It worked beautifully. It was very simple. The control was done by a master student called Bill Fisher, who went on at Hewlett-Packard and worked on high-speed assembly. So that's for the history, but it's still interesting. And then I decided that force control was not interesting because it worked. But somehow, all these years later, people still work on force control somehow. I was under the impression it was a solved problem, but clearly I was completely wrong. And so I'll spend a few minutes. That was my original talk about the mechanics of the fingertips, which are so interesting. I'll just highlight a few things, and if you want to know more, you go on YouTube, because that's where they spend more time talking about it. But in a nutshell, the fingers are naturally adaptable. They have these beautiful viscoelastic properties that make them, if you want, interact with objects in different manners. And that's completely due to their mechanics and their chemistry, by the way, because they are also living organisms. And also, fingers have, of course, we all know, wonderful neural equipment, which allows them to detect some features of the interaction that the skin has with objects. And so that's something actually will be probably explored a little further by my colleague Henrik here. So the point here is that we often talk about sensory integration, but there are many, so the idea of sensory integration that we look at animals or robots as objects that collect information and then try to relate them together into a common, if you want, object or sensation. But
There is another way to look at it, is the amount of perturbation that happens to an animal or robot is so huge from a physical viewpoint that actually the possible mirror problem is actually to take all these things apart and to disintegrate all these different stimuli that permanently bombard an organism. And so I'll give you some, so that's the idea essentially. It's, there's an aspect to perception which is to actually take apart things, and as opposed to put them together. So a bit of a theory. So that's an idea which I like very much, which was inspired by work in vision. The idea is that when you think of the light field, typically you approach it from the viewpoint that it's like an image, so it's a two-dimensional object. But the physics of light is very different from that. The fact that we think of images as two-dimensional is entirely due to the fact that we have optics, or we have a particular lens or a particular hole that will project an image. But in itself, the light field is much more complicated than two-dimensional. And it's now well accepted that it has really 7 dimensions. There's really, you need 7 numbers to be able to talk about it. It's simple to think of it. If you have a space, then you can observe the light field from a point in space, which gives you 3 freedoms. And you can look from that particular point in any orientation, which give you 2 more numbers, that gives you 5. And then of course that depends on time, and it depends on wavelength. So you have a total of 7 numbers, which actually is the simplified physics of the optical world. It's not 2. So the question is, when you are manipulating or touching object, what is that number? Going back to the physics, the idea is to look at the basic phenomena, and then what we can accept is that what is universally the case is that 2 objects which are elastic and touch do not interpenetrate. That's really the most fundamental fact about, if you want, mechanical interactions. And so basically what you can think of now is like if you have a body B like me, and you have a body A which is unknown, like a glass, how do I know that the glass is a glass? Essentially, it's because somehow when I touch it, my body changes configuration. And from that change of configuration, then I have to deduce something about what was the cause of this change of configuration. And so you can put this in an equation if you want. The trouble starts at this point. It's because bodies are made of an infinite number of points. So the description of these deformations require infinite number of coordinates to be talked about. So that's why there is a question mark in the title of the paper, because it's very hard to talk about the set of all things that you can ever feel. It's really not a question that is easily answered because of this infinite dimensional quality. And in this reasoning, we only speak about statics. So not the dynamics are not even considered. But you can simplify it. Of course, it's clear. Animals or robots or people have a finite number of neurons, so they have to deal with a finite number of things. And so there are some simplifications which are have to be done, and sometimes they are done spontaneously, not even thinking of them, but they are done nonetheless. The most common is actually to suppose that when I touch something, there is a deformation that's only in a small neighborhood. So there are mechanical reasons where that happens in most of the time. Sometimes it is not the case. Sometimes it's true, sometimes it's not. But it's true most of the time. And if you can assume that small deformation, then you can simplify your contact by a few numbers. If you want the angle or an approach and the amount of penetration, and then you can simplify the interaction with one single number, which is typically done when you do computer simulation of so-called computer simulations. But of course, there are many other cases which can be useful. The most important, the one that's most natural, is to believe that all objects are rigid, including the toucher and the touched. And in that case, the problem simplifies a lot. It's what you do in a mechanical workshop. When you have a caliper, you make object in contact, and then you suppose that deformation is 0, and then from that you can deduce something about the geometry of what you're measuring. But if you don't make that assumption, it's something else happens, clearly. And so you have all these different cases which are possible. And of course, mechanics are very complicated. They have things that are different from optics. For example, the fact that when you touch objects, you can induce changes that are permanent, or they are you have also changes which are that depend completely on the trajectory. When I look at something, the thing doesn't change according to how I move, but when I touch, it does. And so that's a good example here. When you try to detect a tumor, which is embedded in the tissue, then you have it's a sensory strategy, which is actually to move in two different ways. So if you move, like in the first row, you go down and you push the tumor on the side, then it ends up on the right hand side of your finger. But if you slide on the surface and then push down, then it'll be on the left side of your finger. And that alone tells you that there is an inclusion inside the body. So that's sensing option, and it's no wonder why in nature there are so many of these haptic organs. These are 3 examples, but of course every animal has developed different sensory organs. Practically every species has, from insects to birds, different ways of probing the mechanical environment. And of course, primates on the left have their own idea about what is useful to probe the mechanical environment, presumably because of manipulation. So here now I'm going to go through a few examples of which are I found interesting. They are classic, but they really show that this lack of separation between, if you want, what intuition will tell you about what is sensed. So the first example I picked is this one. That was discovered by colleagues in University of Louvain, and they discovered something really interesting. Working in a hospital, patients who had their hands reattached after amputation or after accident for unexplainable reason were capable of tactile performance, which has a similar level as a healthy person in terms of texture detection. So that's really mysterious, because every textbook tells you that textures are felt by the skin. And so that was interesting. So we went ahead and then measured the mechanical noise that happens higher in the anatomy when you manipulate things. And then what we found is actually that far away inside the arm, there is a very measurable and probably very large amount of mechanical activity, which basically means whenever I touch an object, I do this, the entire arm is actually responding to the contact. If I slide or tap, and so that's interesting. How does the brain manages to tell that it's coming from this particular origin? So you can look at it as an acoustic problem, actually, of source localization, which is probably what I would imagine is really the case, and explains why these patients, having no sensation in the hand, would behave so beautifully. So that's one example.
You mean that to some extent the person wearing the prosthesis would...
Absolutely. And there are plenty of examples of that, yeah. But let's not get sidetracked.
Okay.
Second example, this is very, that's a classic illusion. It's really a fun, I'll need it later actually. You can do it at home actually. It's very, how do you feel that an object is wet or dry, okay? So you can think that it's sort of a mechanical effect. But of course, definitely, the tribology of the skin varies enormously according to the level of wetness. But in this experiment, it's very clever. What you do, you also listen to the noise the hands make when they rub. So this noise, okay? And basically, what is done here is that you accentuate the high frequencies during this act. So you can do it at home with phone speakers and an equalizer and then accentuate the high frequency. And what you feel is your hands becoming dry, okay? So that's, and it's very powerful. And you can see, you know, the results are totally clear-cut. And when there is no need for actually reading the paper, you can do it at home. It works very, very efficiently. So again, this tends to show that there is not so clear a distinction between hearing and touch. So we'll come back to that later. Third example, which is one of our colleagues has found a few years ago. It's often believed that we're aware of the position of our fingers or limbs because there are somehow sensors in the muscles that tell us where the fingers and limbs are. But what Benedin did is actually anesthetize some regions of the finger, and then by manipulating unbeknownst from the owner of the finger, then the owner would feel the finger moving, when in fact the finger was immobile, but the skin was moving around the joint. Okay, so this is also very much contrary to intuition, or at least what's written in most textbooks. What it says is actually when at least you move your extremities and arms, a great deal of the information about the movements come from the movement of the skin, which normally is there for something else. So that's interesting, actually. So so that's really part of this interrogation problem I was talking about. How on earth the brain manages to sort out all these different sources of information and distinguish actually position of an arm from a sensation about an external object, for example. So this is a third example, which I like very much. Now we can look at functional examples. This is a totally classic, and really interesting. When a person stands, it's impossible to stand quietly. There is always some residual movement for keeping balance, even if you stay quiet like this. And it's well known that if you close your eyes, then the orbiting becomes bigger. Okay. If you have problem in your vestibular system, same thing. Because actually standing is one of the most beautiful examples of sensory integration. Everything in your body participates to standing properly. The feet, the hands, everything. And so the experiment is very nice. All you do here is like you become blindfolded, your orbit becomes bigger, you touch immobile objects, and it reduces by the same amount as you were looking, quantitatively. So basically you just do this, and that's sufficient to give enough information to the brain for restoring the same, if you want, the dynamic equilibrium as if you were looking. Which is a very good case where actually you have vision and touch are basically doing the same function. And that's reason to think that actually the brain doesn't care if, you know, for standing, whether it comes from the eyes or the hand. It's really very much the same thing. So that's really not a question of integration. It's really that's another example here. That's something we did. It's a follow-up of work done by Flanagan in Canada, who had noticed, and following Goudet also, that you know, in behavior you have, it seems like the brain has two different pathways or two different functions. One which is for perception, one for action, and then basically one can act differently from the other. And that can be tested through illusion. So you can induce a perceptual illusion, but there's no motor consequences. And so we did verify that fact again, once again, through another illusion, which is pretty interesting, which is the fact that whenever, it was well known actually that bigger objects feel lighter, but it's also the case that bigger objects feel lighter even if you have no gravity. If you manipulate without the gravity load, the brain is smart enough to be subject to the same illusion, actually. So bigger objects feel lighter, and there's absolutely no consequence on the gripping behavior. But here, what is interesting is that you have 3 to 4 orders of magnitude of difference between the gravity and the inertial case. So it's very different mechanics, completely different, and yet the same result. I'll finish this series of examples by this one. That's with Alex, who is sitting here. It's a rather provocative title. If you want the accepted view of how the brain or knows about the position of limbs, it's because it somehow through the skin or through the muscles knows the joint angles. Okay, that's how you. So here we have an example, and basically we have a situation where actually the sensation of movement or position of your limbs in space depends on what you touch for the same position. And so that's how we went about to show that. We have 2 cases. We are stimulating the skin with different signal. I won't go into the details, but they are in every point identical for small details. For one small details. And in one case, then the sensation of movement occurs and not in the other. Okay, so the change of details essentially has to do with what we think is certain regularities in the world, certain properties of mechanical objects which normally behave according to certain laws. And if you break that law, then the information is blocked or is not processed. So that's how we call that effect. Extrasomatic means that basically you know where you are because of things that are outside. So, for example, if I put my finger on this table, then I know my hand is not moving because the table is not moving, essentially, and not the other way around. It's not the table is not rigid because my hand is not moving. It's because my hand is there because the table is not moving. So it's a different way of thinking of this relationship between action and perception. And I'll skip that for interest of time, and I'll just show a little piece of physics along the same line about this idea that the brain is probably not particularly interested in sorting out what particular sense gives information. And it's a very simple idea. This is the classic plot which tells how your hearing system works. So, or at least how efficient it is. So it says basically if you move air particles of 1 micron, okay, then you have a detection threshold, okay, and that depends on frequency. Okay, so in audition, then as you go higher in frequency, then you become more and more sensitive to small displacements. Okay, so that's a constant displacement. So you have this yellow curve here, and then you have a super sensitive ear at that particular frequency, then it goes a little worse. So that's for 1 micron of movement. And then in touch, when you touch an object, you also feel it moving, and then you have a threshold of detection, which is for 1 micron, and it covers that frequency range here, and the 2 curves meet here around this, say, between 10 and 100 hertz. And so that's interesting. That intrigued us a lot. Like you have this continuous continuum between touch and audition about detection of small movement. But then you can look at this data in a completely different way. You can replot it this way with physics in mind. Because it's not so interesting to tell that things are moving 1 micron. What is interesting is things that you deal with. And what you deal with are things that are objects of different sizes. And size in acoustic matters. A small object only radiates energy in the high frequencies. So here we basically plotted the same data but in a different manner in terms of the acoustic emission produced by a bigger object, something that's about that big. Okay, and then so now if you have this bigger object, then clearly the threshold shoots up when you go when in a low frequency. You can't hear it anymore. Okay, and at the same time, if you do the same plot, you realize that touch is incredibly good. And in fact, touch can detect things that are moving that are really small, where hearing is completely inoperative. And really, these two, it's very interesting because actually this region where the two curves cross is really basically where touch takes over. So it's as if we had evolved to have touch and audition to cover a spatial scale and a frequency scale which is continuous. In other words, things that are small cannot be heard because it's physically impossible for them to move enough air for the ear to pick up. But when you have them on your skin, there's no problem. You can detect them easily, very easily. So essentially, basically, it's as if the brain has evolved to have covered all these physical scales from sizes, probably distances. That's a particular distance. So if you change the distance, then this curve would shift. So we'd have the and essentially it could be viewed essentially that it's the same time addressing different scales. Small things have to be touched basically because they make no noise. And it's all mechanical. So basically, there is only one mechanical sense. It has, if you want, two transducer organs, but it's still one single mechanical sense. That's the way you could think of it. And an easy way to see how it's, that's another way to plot the same data. Basically, you fix the frequency this time, and then you have a constant auditory level, and it basically tells you that small things cannot be heard, but they can be felt, essentially. So with that, I think I finished my disintegration problem. And if you have questions, then... Which graph? Oh, this is totally theoretical. I mean, it's not theoretical. It's well-known data, but we plotted it in a different way. That's all. Yeah. Yeah, all these thresholds are well known. I mean, the textbooks are full of them, of these thresholds. It's just a matter of replotting it according to physical laws, according to the manner in which mechanical information propagates through solids and gases, essentially.
Are there any other questions? Don't be intimidated by Vince. He only accepts questions.
Yeah.
So there was a talk where you showed, you didn't have time to discuss the details of the protocol, where you had the tactile display going in this direction, this direction.
Right.
So what were the subjects asked to report? Whether there was a a given stimulus?
They will ask to report their own sensation of limb displacement.
Okay, so after the stimulus, you take the hand away, and then you have them to put it where they felt the stimulus, or?
Yeah, you put your finger on the surface. You push on the surface, and then you report how much movement is felt.
Oh, okay. So.
If you want to try it, you can come.
Okay, thank you very much again, and.
Yep. Same one. Oh yeah.
We move to our next speaker, who is Henrik Hjortel from Lund University. It's neuroscience for robotics, not for dummies, but for robotics. And what do we need to know?
Is this good enough? Yeah. Thank you, Antonio. And thank you for organizing this interesting type of meeting. Okay, so before I start, I would like to give some credit to Martin Nilsson from Swedish Institute of Computer Science sitting up front here. So a lot of the concept that we have developed is basically coming from him or from close collaboration between Martin and our group. So before I start, I would like to just tell you the background. So we are integrative neurophysiologists, which use a relatively unique technique, which is the in vivo whole cell recordings from animal experiments. And although there are a few other groups in the world that uses the in vivo whole cell recordings, I think there are no one who uses this in a more systematizing type of approach. And we think that this systematic approach using this technique, which makes it possible to reconstruct the network structure, and that is the state of explanatory power that we want to reach with our research. We want to understand how brain mechanisms are carried out at the mechanistic level as opposed to the descriptive level. And also, I have had the pleasure to collaborate with people who are more closely related to robotics than neuroscience for a relatively long stretch of years now. And I found that work very rewarding, because working with roboticists, it forces you to think in terms of closed loops. So you have to take responsibility. If you model a system that creates output, it will, of course, also it will affect the feedback or the responses that you obtain from your system. And if you don't pay attention to that, those feedback effects, you will, in the end up in a system that you have not understood properly. And I think this is a major problem in neuroscience, per se, that people tend to create theories of function without taking responsibility at the closed loop level, and that has created a lot of strange or maybe unfounded ideas which tend to become viral. But working with roboticists, I find this is not a problem. So what then is the link between neuroscience and robotics? Well, the brain naturally evolved for the sole purpose of allowing movement. And evolution has been driven by the need to find more effective ways to utilize movement to increase survival. And robotics is, of course, then first and foremost about movement control. But what about the other way around? What use have roboticists of neuroscience? Well, I can first say that it seems to me there's a self-defined need, in a sense, because there's a lot of groups around the world that strive to copy effects that we have in humans and in biological systems. But my own thinking is that there is a need to understand neuroscience, because the brain, it manages to combine speed and precision and versatility of movement control, which we are not even close to approaching robotic systems today. So, a first, perhaps surprising insight is that the central nervous system, or the brain as we usually refer to it, has very much a similar working plan to solve control in a long range of vertebrate species. So this picture shows you a lamprey, which is a very simple form exerts a very simple form of control. It basically has no movable fins, so it moves like a snake, but in water. So it can swim forward, and it can actually swim backward, and it can turn a little bit to the left and right, and that's basically its movement repertoire. And but many of the structures that we have in the human brain are present also in the lamprey, or I would say almost all structures that we have in the human brain is present also in the lamprey. Of course, the amount of neural tissue differs vastly, but in principle, the same functional structures are present in both these species. So if I had replaced this lamprey with a whale, for example, then we would have very, very similar nervous systems. But I think we would all agree that the motor functions carried out are very different. Okay, and another thing is that if we look in the same species, we utilize the same set of structures to achieve very different kinds of movements. So these are two very relevant examples, and so I think the lessons from these two slides, not yet. All right. So the lessons from these two slides is that we do have a fundamental brain or set of brain structures, which can achieve vastly different kinds of movement control. So the question then arises how this can occur. So an interesting observation is that when you look at the embryonic development of many different kinds of animals, and in particular if we confine ourselves to mammals, the development is indistinct, and you can't distinguish different species up to a certain age. And it goes both for the body, the development of the body, but in particular then today for the development of the central nervous. So it would be hard to distinguish this central nervous system from a human from corresponding developmental stage in a mouse or a whale, for example. So then during embryonic development, we start to develop limbs as humans, and that is seemed to be a decisive stage. Then things start to develop differently in the central nervous systems. And this is now a bit speculative slide, because we know very little what's going on at these early embryonic stages. We decide to know more, of course, but we can just look at the types of sensors that we have in our bodies. So for each limb, we have in the order of 100,000 sensors. We have a wide set of types of sensors. So in the skin alone, we have a large number of so-called tactile sensors, which exist in different varieties. There are, in addition, other types of sensors in the skin which have a more protective protective function. Whereas in the muscles, we have sensors for sensing force. We have the classical spindle sensors, which are not, in contrast to textbooks, the ideal proprioceptor, but they have a much more advanced function in the central nervous system. And we have other types of muscle sensors which have more chemical nature, which is again then for a protective function. When we overuse our muscles, for example, we need to slow down activity level not to destroy the muscle fibers chemically. So all of these sensors, they grow during the embryonic development. They grow into the central nervous system by aid of chemotaxis. So this is now a genetically defined process. So during embryonic development, we have a lot of chemical compartments that arise in the embryo. And those chemical compartments send attractive signals to certain type of fibers, which make them grow into that structure or that part of the central nervous system. We also, quite early on, has learning processes that is active, and whereas the chemotaxis attracts the fiber, the actual targeting of the synapse, in particular the adaptation of the synaptic weight, which is a very important process to define the function of the circuitry, is probably more or less completely defined by learning processes. And we are here maybe talking about relatively straightforward and simple classical Hebbian learning or varieties of that. So in addition, but actually a bit later on, we have ingrowth of motor command signals from the neocortex. But before that happens, we have the establishment of the low-level sensory motor contingencies, which means, when I'm saying that, it means that the sensory fibers, they have powerful connections with the motor output of the central nervous system. And that is what is established first, and then the neocortical system is more or less forced to accept this fact and have to adapt to the properties that have been laid down at an early developmental stage. And presumably this is a ever-evolving story. So during the post-natal development, this process continues. We presumably have continuous adaptation and learning in this sensory motor contingencies. And at the same time, the corticospinal system tries to gain control of this system, which is apparently a very difficult process since it takes a very long time. Okay. So the previous slide then showed that the motor functions of the brain is to a large extent dependent on the sensory feedback. So there are probably sensory motor effects that are more or less impossible to suppress, and the cortex or the other motor command system have learned to adapt to this established fact. But interesting, it works also the other way around. So the sensory information that we receive from the periphery and the part of that sensory information which is propagated up to the conscious centers is modified by cortical and brainstem outputs at multiple different levels. So the cortical and brainstem outputs are, of course, motor command signals. So this means that all the sensory information that we gain is continuously evaluated and filtered against the ongoing internal activity, which is basically motor command. So I'm switching subject a little bit now. So this slide will be about the development of the concept of brain organization in movement control. And the first, basically the first concept that arose was the topographical organization of the motor cortex, the M1 motor cortex of the neocortex. And this picture stems basically from the 30s or 40s, and it was established by Penfield in the 50s, where he could make the direct demonstrations of this in neurosurgical patients. So it's a very catchy image, and for a long time I think people did not really ask the question what it really explains. But after 30 years or so, we started to arise question what is actually, what's the functional contribution from these areas. And of course, the question or the desire was that it's going to be some easily interpretable physical parameter, because that is would make it much more easy to understand. But I think as we're moving from the 80s, when these first recordings were starting to be made, we have seen almost as many interpretations of the coding as we have seen investigations of the motor cortex. So I think what this is telling us is that we don't have an explicit representation of any physical parameter, which of course can be explained by that this cortical signal is being transformed by the sensory motor continuities present at this subcortical level. So depending on context, the output of a new cortical neuron can have very different effects. Okay, and then also more recently were some very clear evidences that this original envisioned topography of the motor cortex simply do not hold. And I think the real groundbreaker here was a Japanese group led by Professor Chinoda, who demonstrated this directly by the branching patterns of corticospinal axons. And this has been followed. It took some time for this concept to be widely accepted, but now I think there is different techniques that shows that individual muscles have a very wide representation at the level of the neocortex. So even this relatively simple idea is still a matter of controversy. So what is actually being done by the neurons in the primary motor cortex? So another issue of with some controversial or potential controversial value is the very recent development where there's been developed genetic markers for different kinds of neurons. So these genetic markers, they arise again through embryonic development, and since they arise from during the embryonic development, the question has of course been, if this is a genetic blueprint for organizing the neuronal circuitry, and therefore these genetically specified neuron types should have specific functions. So with the birth of the genetics tool, you can of course probe the functions of these individual subtypes of neurons. And these papers have come out only this year, and we'll probably see more of them in the upcoming future. My personal reflection so far is that the genetically specified neurons do not seem to carry any highly function. So it more comes down to that the brain produces its effects through an interaction between a large number of neurons, and if you take away one population, you will not obtain any specific effect, but you will have some marginal defects in the capacity for motor control. Okay, and then a final slide illustrating another issue of controversy in neuroscience. If we want to understand how the brain works at the mechanistic level, we need to understand how the brain represents information. And the key step in that field is to understand how the information received from the synapses, it's summated according to the classical Hodgkin-Huxley models, but how are this information converted into spike outputs? And this is something that neurophysiology has been dealing with for at least 60 years. But I would say that this issue is still not yet completely solved. Yeah, okay, so thank you for your attention. Yeah, so if you take away a subpopulation of neurons, you will either have, I mean, of course, if you, depending on how far you stretch it, but if you take away a subpopulation of neurons, you will have marginal effects on the motor control. Of course, if you take away a sufficient number, you will start to see severe deficits. But I think from these genetic manipulation experiments, you will have some perturbations that you could explain by that you have removed, part of the processing population. You don't have any threshold effects, so to speak, that you remove any particular function. Yeah. Yeah. No, it's in particular true for other body parts. So I think you have a much larger part of the motor cortex devoted to the hand. So it means that you have, in a way, a more limited number of muscles that are represented across a wider area of cortex. But I think, somatotropy within, amongst the hand muscles, I think there are direct evidence it does not exist because yeah. But I would say that the divergence, so to speak, of the corticospinal tract axons is the smallest for the hand representation, but it's still there.
Gold. Scattered from the Vrije University in Amsterdam. The talk is about Haptic search for Saliency.
Maybe here. Okay, good afternoon. I first want to acknowledge the people who really did the work. So these are Meerte Plezier, Wouter Bergman-Tiest and Van Polane. I work on psychophysics, so it's quite different from robotics. But I'm also involved in the project that will be presented tomorrow and where we have been working in for 4 years. And our research topic was the haptic search for salient features, and this might also be or it turned out in this project, relevant if you want to design robot hands or prosthetic arms. So you want to know more about human performance, what is important for human touch, and that's what we put in this project. So we are looking for salient features. Which are the salient features for touch? Now, there was a paradigm that has been used for many, many years in vision, and that is a search paradigm. So if you want to, for example, if you look here and your task is to decide as soon as possible whether there is a red disc among the blue ones, then you see it pops out. You see it right away. You do not have to look at all the individual discs, what kind of color they have. No, you see right away there is a red dot. And the same here, if you increase the number of blue discs, you still see right away, unless you're colorblind, of course, that there is one red dot. And if it's not present, then you also see it immediately. You do not start looking for it. No, you see right away there is not a red disc. So this is called what we this is termed parallel search. So you do not have to look at all the individual items. You just see it right away, and you can increase the number of distractors. And here is the response time, and you see more or less a straight or a horizontal line. So that's one thing that you should remember, because that comes back in my talk with the results. Now, there are also situations where it's much harder to find something. So, for example, here, if you have to decide, is there an O among the C's, it takes you more time. You still are quite quick, but it takes a little bit of effort. And now, if I increase the number of C's, like here, it will take even longer. So in this case, it's not a parallel search, but it is a serial search. And you should also remember this. So if there is a slope, a significant slope, when you plot the response time against the number of distractors, then there is not a serial, then there is a serial search. This we call pop-out, and this well, is clearly not a pop-out. Now, we were inspired by this visual perception research, and we decided to do similar things in haptics. So what I'm going to do this afternoon is to give you an overview of the kind of things we did with this paradigm. And what you see here is that we have a stimulus which consists of a number of, these are all patches of sandpaper, but one patch, what you see here, is different. So they differ in roughness. This one is very rough and the others are quite smooth. And again, like in the visual experiments, the task is for the observer to, well, to decide as fast as possible whether there is a different roughness patch or not. Now, if we make the differences between the roughnesses smaller, then you get something like this. Again, the task is to do it as quickly as possible, but in this case the difference is much smaller, and then the participant really has to go over all the patches until he or she, in this case she, recognizes there is this patch. So that's the paradigm we use. How do we do these experiments? Our subjects are always blindfolded. And what we do is that there is a line here, and that's some metal. And as soon as the subject touches that metal strip, then the reaction time starts, or at least the measurement of the time. And as soon as the subject decides yes or no, there is a target present, the time stops according to the focal response. And what we analyze is the response time and also the movement patterns. In the 2D case, we use stimuli like this, so for roughness, so and the roughnesses could vary, and of course also the number of distractors varied from trial to trial. And here we have another example of movability. So these are ball transfer units that some of them we glued, and subjects had to move over it and again decide whether the one moving or the one not moving was present or not. And these are the kinds of results we get, like in the visual case. So this is an example of the roughness. So the task was, is a different roughness patch present? And depending on the combination, so for example, combination A is rough among fine, so that's a really large difference. Then you have a pop-out because the reaction times almost do not depend on the number of distractors. But if you make it harder, so for example, if you have to look for the very smooth one among a lot of rough ones, then it's much harder to find, and then you see that the reaction time increases with the number of items. So this was one of the first cases where we could show that there is also pop-out in haptics. So that means that roughness is very salient for touch. And you can look at the reaction times, but you can also look at the movement patterns. So this is an example of the pop-out. Subjects sweep their hand over the stimulus display and they decide it right away. If it's harder, then, well, sometimes they are lucky, they find it again very fast, but most often they really have to go with their finger from item to item. And here you can, for example, you can see the sensor was fixed to the index finger. The index finger doesn't even touch the patch, the target patch, but also with the palm of the hand, the subject could determine that this rough patch was present. So that is, this is another way of looking whether roughness is salient or not. Then these are very similar plots, but for the movability case, and there it's also if it's a salient combination, so the easy search, then there is a fluent movement, and in the serial strategy it's very detailed movements. Now we also wanted to go to 3D experiments because, well, of course, judging texture is something that is used in touch, but mostly we touch three-dimensional objects. And this is an example of our setup with three-dimensional objects. So that in some situations, like here, there is a cube among the spheres, and again the task of the subject is to grasp all the items and decide as soon as possible whether this cube is present or not. And we vary the number of spheres. And again, we in our setup, as soon as the subject touches the stimuli, the time measurement starts, and as soon as the subject gives a focal response, yes or no, then the reaction time stops. And what you see here is the results. Here, for the conditions that there's a target present, and you can see we have very, very shallow search slopes. So again, there is pop-out, and in this case, the target is absent. Well, of course, it's harder to decide whether a target is not present than when it is present, because if it's there, then once you have touched it, you know it's there. If it's not there, then it can still be that you have missed it. So also in vision, it always takes longer to decide that the target is not present. But here the slope is quite steep. So what we find is that there are very fast responses if the target is there, and especially in the case where there is one cube among spheres. That's a very salient feature. And what we find from this is that edges and vertices are very salient to touch. Now, we over the years we went from feature to feature, and here we also studied compliance. What we had to do was to create our stimuli ourselves. So these are some molds, and we have rubber which we could put in it, and then our PhD student Vonne van Polane, who defended her thesis last week, had to move it, and at the end we had lots of stimuli, which you can see here. Of course, our subjects are blindfolded, so they don't see the color, but the white ones are the very soft ones and the red ones are the hard ones, and I can show you how that looks. This is not an actual experiment, but this is just to show how the stimuli are. So this is a very hard one, and the other one is clearly very soft. So that's what I have to distinguish. And again, the task is to grasp them, and in this case to decide whether the hard one is present among the soft ones. And what we see here, that's another feature that pops out. So also if it's hard among soft ones, it pops out. And here we have a soft target. This is in the 2D case, so we also had an experiment where the subject had to, this is all 2D, what I show here, sorry. So all the items were fixed on this plate, and in the case of a hard target, it popped out. In the case of a soft target, it did not pop out, and you can imagine why, because all the hard ones prevent your hand from feeling the actually soft one. And these are the results for the 3D case. And although this is the case for the hard versus the middle soft, so the difference is not so big, then there's clearly no pop out. But if we make the difference bigger, so hard versus soft or soft versus hard, in both cases there's a clear pop out effect, so hardly any influence of the number of distractors. And of course in touch, the number of distractors is determined by how many items you can hold in your hands. So it doesn't go on infinitely. So here's a summary of what we've found so far. For the feature saliency in haptic search task, roughness is a salient feature. Shapes can be salient, especially cubes. They pop out among spheres, and edges and vertices are very important. What I did not show you, but what we also did, is that we varied the temperature of the items. So we had a piece of ice, and we put the cold ones on it, and we had warm, something that we could hold them warm, and then we found that the cold items pop out. And of course the reaction time had to be quick, because these are metal bars, so if you hold them in your hand for a while, then the temperature difference vanishes because of the warmth of your hand. But in the case of cold items, they popped out. And then in the case of movability, that could also pop out. So if they were movable, then they popped out among fixed, not the other way around. So if all the items could move and one was anchored, then it was much harder to find. And here we have the compliance. And this, in vision, these experiments have been going on for many, many years, and what they decide on the basis of these experiments is that they learn something about, or they teach something about what are the primitive features. And well, apparently features like these are primitive for haptics. There's one warning: saliency is relative. So if you, it really depends on the difference with the distractors. So if you have a very rough item, it pops out among smooth items, but it does not pop out if the other items are also relatively rough. And also, saliency is not always symmetrical, so it can, well, the cubes among the spheres was easier than a sphere among cubes. So that's what I wanted to tell you, and if there are any questions, I would like to hear them. And again, these are the people who actually did all work with me at the background. I noticed a question there. There was a question there. There.
Hi, thanks for your talk. I had a question about, you were mentioning that the movement pattern changed when...
Come forward, I have difficulties hearing you.
Okay. Is this better?
Yeah.
You were saying that the movement pattern changed when it was not a pop-out?
Yeah.
I was wondering how many trials you had per condition, and if you saw that movement pattern evolve, if there was a learning effect to the movement pattern.
We always give them practice trials in advance so that so we hope to avoid learning during the experiment, but we did many trials, so there could be some learning, but that was to optimize the task.
Okay, but did you look, I'm just curious how the learning...
No, we did not analyze over time.
Okay, thank you.
But the difference between pop-out and not pop-out is very clear.
I think we can take a coffee break now. And
first presentation given by Domenico Fatichizzo from University of Siena. Please, Domenico.
Okay, so thanks for inviting me to this jam session. And I'm going to present this new idea that we are developing between Siena and IIT towards a new paradigms of human-robot integration. Okay, so if you, and this is a joint work with Monica Salmaldezzi, Jonathan Salvietti, Simone Rossi, and recently also from people from Pisa, like Emiliano and Andrea. Okay, so if you, actually I need to plug this one, sorry. If you think about to the integration of humans and robots, then typically we already discussed many of these, like exoskeleton. This exoskeleton developed at IIT, or prostheses like the Touch Bionics iLimb. So you try to either to replicate the structure, the kinematic of the human hand or the arm or the legs, or you try to substitute it by using device for amputee and other things. Actually, the talk that I'm giving today is to go beyond exoskeleton and prosthesis. What means to go beyond exoskeleton and prosthesis is explained in this video that is interesting to see. If you look at this video, you see a hand with a sixth finger, and the sixth finger now is in a bracelet. You will see in a moment. There is a human hand with a sixth finger which is worn by the subject, and you see that in a moment the sixth finger is a second thumb actually, and the sixth finger goes towards the objects and tries to grasp the object in a new way. So there is a new way of cooperation between the human hand and the robotic fingers, which is completely new with respect to the exoskeleton and prosthesis. Now, this is really work of that, I mean, we started developing in our labs since a few years, but we published this, we presented this the first time last week to the IEEE ASME conference that will be going to be presented in Rome this year. Well, if you think about the impact of the augmented human hand, so think about the application. What are the applications? So one application is really natural if you cannot use a prosthesis. If you have a stroke, if I have a stroke and I have the hand, but I'm not able to grasp objects anymore because I have no control of the thumb, then probably I need an additional finger, an additional thumb to recreate the grasp, because I'm not able to use for the stroke the human hand anymore. And I cannot use the prosthesis because the hand is still there. Another application for impaired people is for people with the thumb with severe arthrosis. They have pain in using the thumb. So we can support the grasp for older adults with this additional thumb, with these additional extra limbs. And of course you can think about finger amputation, which is very, very natural. But also you can think about healthy people. You can think about to previously impossible grasps. You can grasp larger objects, or you can grasp two things with a single hand, because you have a dual grasp scenarios. And also you can improve productivity and comfort in heavy tasks. And of course, this is something that I would like to think about. I think that if we develop technology for people without impairment, we also help people with impairments, because we have for sure a larger market. I am always thinking to the iPad. iPad are developed for us, but now are used by people with visually impaired to zoom and see many things. So technologies for all the people that are very useful also for people with impairments. Well, think about the anatomical impossible grasps, as I was showing you before. This is a scenario where there is one of my students, Irfan, who is using the additional thumb to grasp larger objects. And you can think about to grasp larger balls or larger box and whatever you can imagine. So anatomical impossible grasp becomes possible this time because of this additional thumb. Well, The literature is very poor in this field, in the sense that there has been very few work. And in particular, I'm referring to the work of Asada and this group, and they are working since 2012 on extra arms to support subjects to make heavy assembly parts. So you have more arms to coordinate. And actually, Asada is working, I know that he's also working on extra fingers to work on this. But our focus, our contribution here is on extremely wearable robotic fixed finger to have new grasping scenarios, which integrates robotics and human hand. Well, so we are talking about embodied extra limbs. It's not the classical human robot interaction. Here you can see a work by Chan, the University British Columbia, when you have hands-over cooperation between a robotic hand and a human hand. But it's not embodied at the level that we are thinking with the sixth finger. So these are two subjects, a robotic subject and a human subject that are cooperating. We are thinking to an extremely wearable integration and a natural human-robot integration. So the design of the sixth finger, some mechanical specification. We are using the same kinematics of the human finger, 4 degrees of freedom, one for the adduction and abduction. So there is a joint here which makes adduction and abduction, and there are joints here with servo motors for flexion and extension. It's extremely wearable because I think that technology should be wearable, otherwise we don't use too much. And of course it can be improved in terms of wearability, and the joints are actuated. And it's also a modular design, so you can add additional modules to have more complex fingers or simpler fingers. Well, human-robot coordination. So the focus of the talk is, okay, now how can we try to map the motion of the robotic finger with the motion of the human hand? So how can we control those human robotic device? Well, we are thinking to something very, very natural, and we did, actually, within the end embodied, we did a work that has been published last year on transaction robotics, and you also generalized the approach in the current ICRA, where we map the human hand on a robotic hand, typical teleoperation scenarios. Human hand on one side, robotic hand with different kinematics. Well, the story here is different, because the story here is that I want to map the human hand onto a codomain which contains the domain itself. So now I want to map the human hand on a structure which is the human hand plus the robotic hand. So the big difference with respect to previous literature from our group is that now the arrival domain, the codomain, contains the domain itself, because it's the human hand. And this is the contribution that we gave last week in IEEE IM conference. We were, again, this is the story, joint to joint, fingertip mapping. We love the object space mapping, the task space mapping, and this is the story. If you think about how we map the human finger to the robotic finger, then simply just let me go to the points. Consider the fingertips and focus to the fingertip mapping. You can also take some other reference point, but take the 5 fingertips plus the 6th fingertip of the robot, and build a sphere around these points, a virtual sphere, a virtual objects. You have the point. You can take the minimum volume sphere. Then you move the hand. If you move the hand, then you deform the sphere. Okay, because as you move the fingertip of the hand, then the sphere becomes smaller, because the sphere contains all the fingertips, including the robot fingertips, but is the minimum volume one. So if you squeeze the hand, so the sphere, the virtual objects, deforms. It deforms with rigid body motion plus a deformation, which is captured by the translation of the center of the sphere, the rotation of the frame in the center of the sphere, and the deformation, the changes of the radius. So you can generate from the change of human hand motion this roto translation and deformation. And from the roto translation and deformation, you generate the motion of the robotic hand. So practically, the robotic hand follows the sphere in a certain sense to have the idea. And we did some, so this is the experiment. We were tracking the human hand by the cyber globe. You see, as the cyber globe squeezed, human squeeze, so the sphere reduces and the robotic hand is following it. Okay, so this is the way it's working. Well, numerical simulation, we are using the SynGrasp toolbox, and we added to the human hand the 6th finger augmented robotic human hand. So it's a new model also. This is in the THE toolbox, and we mapped also the first and the second synergies in this case. So if we move the first and second, the human hand by using the first and second synergies, how the robotic fingers perform. And you can see the robotic finger is this one. This is the first synergies. You see, is squeezing, is following this virtual object in some way. And this is the second synergis, is moving towards the palm. And also the robotic finger, this one is following closely. Well, we also did some numerical simulation comparing human hand grasp and human augmented hand grasp of the same object. So 5 fingers versus 6 fingers. And we tested the spectrum, the ratio between the minimum singular value and maximum singular value of the grasp matrix to measure the isotropy. So how easy is for the robotic, for the human hand, or for the augmented human hand to resist the external branches on the object in an isotropic way. You can see has so this is this column, so the larger is the better. So this index, the larger is the better. As you can see, as the diameter of the object becomes larger, then the index of the augmented hand with the 6 fingers doubles the index of the human hand. So this means that for objects, it becomes better using 6 fingers. So this is a sort of evidence, quantitative evaluation of better performance with 6 fingers in this particular case. But of course, if you increase the diameter of the sphere, of course you go in a direction where the object cannot be grasped anymore by the human hand, and you need the extra finger. So you will have an anatomically impossible grasp with the 6th finger as well. You will see it in a while, grasping the cube. This is controlled by the cyber glove, and the fingers move according to the example before, and this is grasping a box, which is also difficult to grasp, of course, with one single hand. Well, is the only way that we want to think about to grasp larger object? We can also think to new kind of grasps, like is what we call, actually today with Simone, we call the ulnar augmented grasp, where you use the 4th and 5th finger, and we use the thumb to make the opposition to the 4th and 5th finger. So this becomes like index and middle finger for the extra thumb. And you can see here in a while, so we control the cyber glove to do this grasp with the ulnar part. And what you can do with the ulnar grasp, you can grasp the object and you leave the couple of grasping thumb and the index to unscrew the thumb. So you can do 2 things with the same hand. So you cannot, I mean, it's something that you can do with one single hand, and this is very useful for people who had strokes and want to improve their manipulability. You can also do some other thing. You can grasp multiple objects actually, and the multiple objects is here, double grasp. You will see you will grasp 2 objects, one with one ball, and the ulnar grasp, and you will use the 3 finger to grasp the other objects. So you will have a couple of object grasping with the same hand. And I'm going to actually conclude my talk. And so we present a new concept of human-robot integration with the 6th finger. So the idea is to have embodied extra limbs, really integrated with human body, extremely wearable, and natural human-robot coordination. Because since it's wearable, so I want to do some control, which makes me using my hand without augmentation very easily. If I don't want to use. If I want to use it, then it's just open and I use it. So the way of using should be natural, to switch between 6th finger on and 16th finger off. And work in progress is to use not only position control but also impedance control according to what I was learning this morning, optimization of the design of the finger placement, under actuation to simplify the design, systematic analysis of more grasp types, like the two-thumb grasps, so you can use two thumbs to grasp something now also in this case, haptic feedback to feel the extra finger, and also EMG. And of course, I think that there are many challenges in design control sensing, sensory motor integration, and the neuroscience. So let me conclude with this give me 6 picture from myself and my group. Thank you.
Have you tried 5 fingers but placed differently?
Sorry?
Have you tried, have you evaluated the grasp you can get with 5 fingers but with 1 finger here?
Yes, yes.
So is 6 better than
this is the evaluation. I mean, we used the ratio between the minimum singular value and the maximum singular value of the grasp matrix is one way of evaluating it. And these columns refers to 6 finger, and these columns refer to 5 fingers. The larger, the better. And here you can see that for larger objects, you can see that this index doubles the index with the 5 finger. So this means that the grasp for the sphere with these diameters are better according to this index for the 6 finger grasps.
So the 5 fingers are placed arbitrarily?
No, we used the grasp planner in the that we are in the toolbox. We are using fingertip grasps with 5 fingers, like grasping a sphere.
If I take this finger and I place.
Ah, okay. So 4 fingers plus 1 here. No, we didn't try. I mean, this is what we did. We didn't try other things. I mean, we can do that, but it's okay.
Thanks. That's very interesting.
Thanks.
It seems like a lot of time we don't even need 5, but one time that definitely you see people using all 5 is the combination grasp. So you were talking about holding 2 objects. It seems like the most common use of that is, you're using a tool, you shift the tool into that grasp, and then use your fingers, switch back and forth. You see that very commonly. And so I'm thinking, this 6th finger might be useful essentially to support, I'll call it tool changing, from the robotics perspective.
In case of LT subjects.
Yeah. So
in case of impairments, probably you can also, I mean, if you don't have the thumb, if it does not work too much, you can have an extra, you can have a...
But looking at it that way, I don't know, it makes me think, gee, I wonder if you're looking at less anthropomorphic ideas. I mean, it's kind of funny because you're using an anthropomorphic finger to build something which is extremely not anthropomorphic. Which is to have 6 fingers. Well, I guess some people do have 6 fingers.
Yeah.
It's unusual.
There is also an animal with 6 fingers. Monica, we found with 2 thumbs. So actually, there is Irfan. If you have just 1 second, Irfan can show how to grasp 2 balls.
Okay, during that time, I have a question about pain associated with this new finger. Have you heard about central clonic pain of phantom limb? So if patients lose a hand or a limb, they still feel that hand representation is in the brain. And in that case, sometimes chronic central pain is associated with a lost limb. So if you ask your subject to use this new finger for a long time, during non-usage, they may feel there exists still this artificial finger, and they may feel some pain associated with this. Haven't you experienced some kind of panic feelings about?
Yeah, we have no yet experience with pain. The only thing that I can say is that Irfan was before in the MRI machine to do some experiment that try to understand what the level of the embodiment of the, and then we will go with the, I don't know if Simone is here. So Simone is there. And so this is why. Okay. Thank you.
Okay, thank you. Thanks again to Domenico. The next speaker is Mark Ernst from Universität Bielefeld in Germany. The title of his talk will be Illusions in Multisensory Integration. What can we learn from them?
Good. Okay. Thanks again for organizing and giving me a chance here to present some of our work that we have recently done together with Alessandro Moscatelli. We got a little bit carried away by watching too much World Cup here. So we're so that's Alessandro. Okay, so let me tell you about a problem, and the good thing to make an analogy to vision. So in vision, if we run around in forest, we probably have an image like that, which is very unstable. And the problem of the brain is, of course, to get somehow a representation, a stable representation of this world that is out there. And if we consider that the brain or the eye is not seeing the whole visual field, but basically that should be an indication of the fovea, you only have a little fovea image, and the brain has to put that all together, this information, from this patchy thing. Of course, luckily we have eye movements, and there are signals from the eyes, how they are moving in the brain. There are signals how our head is moving. And all this can be put together. And of course, what we're also using is much prior knowledge in the scene, namely that the world in general is not moving. If we had a task to figure out if leaves are moving in there while we are running, that's a very damn hard task to do. But if we look at in touch, we basically have the same problem. If we look at the force patterns on the hand that we are getting, which are indicated here on this hand, red means high forces, yellow means medium forces, green or black means no forces, we have the same problems, that we get force patterns across the hand, but they are very much not meaningful as long as we take into account what actually the hand is doing, what are the kinetics of the hand, and what the hand is doing. Then we can start interpreting these force patterns that we have across the hand. This is actually a nice tool developed by our colleagues in Bielefeld in the neuroinformatics group. They developed this sensorized glove here, which has 54 elements of force patches which you can put on the hand, and then you can go around, grasp objects, and look at the force pattern while interacting with the objects. I'm not talking much more about that. I'm going much more simple now, and want to make an analogy to visual illusions, because under very reduced situations, there are many illusions that occur in vision. And what we are looking at is basically whether similar illusions occur in the touch domain as they do in vision when you do eye movements. Because you understand the computational mechanisms behind the integration between tactile inputs and kinesthetic inputs in principle. So let's have a look at one of these illusions in vision. So what your task is basically look at this dot here and follow it with your eyes. It's a very simple task. I'm sure you all could do that. Let's try to do it once again. Okay, now there was a dot pattern appearing. Was that dot pattern moving to the left, to the right, or was it stationary? Who says it's to the left? Who says to the right? Who says stationary? Very good. Okay, let's look at that without eye movements. Oops, did you see it? I have to redo it. it's actually moving this way. When you do an eye movement, you basically have no idea. It's basically for you, it's put it in a way so it's basically seen as stationary. Now we were asking the question whether the same thing happens in touch. So we developed this apparatus here, which is basically a strap where you can put your finger in, and we basically put one of these tools that you get for sanding off the, what's that? I don't know what's the English word. It's a Bandschleifer, we call it in German, where we want to replace the sandpaper in here with different forms of belts that we can put in there. And then you're basically going over the surface, and the surface, of course, is moving. And your task is always to say, is the surface moving to the left or to the right, or is it stationary? We used a slightly different device for the data that I show you now in collaboration with Vincent Hayward, but the principle is the same. The idea is you have a moving surface, and your hand is moving, and you have to judge in which direction is the surface moving. And when you do that, you basically get exactly the same effect as in vision. The red curves is the shifted curve, so this is the PSE now for two different subjects. In this case, the control condition when the hand is stationary, and the red curve is when the hand is moving. This is for the 2 people, this is for 10 people, the average. So if you're moving over that surface, you get a nice effect, a change in the perceived direction of that. So stationary is not stationary anymore, but you need some motion in the opposite direction for you to make it perceptually stationary. Okay, we can do this across the entire space, and we can basically look at the interaction between the handle velocity, where your finger is moving, and the belt velocity, and you can measure the entire space. There's a nice parametric variation between these different 2 conditions. So basically that's pretty much like in vision, but we know in vision much more. Namely, there are several models put out in vision why that may occur. One old model basically says there's just a gain factor, whatever, between different sensory modality, that's a fixed gain. Another more reasonable model is that what we know in vision about motion encoding is that it's dependent on spatial frequency. If you have high spatial frequency, they're usually perceived as faster than if you have low spatial frequency. So there may be some dependency on spatial frequency. A third model that was put out recently about that is a Bayesian model, integrating this notion that usually the world is not moving, and if you integrate that, you can come up with this kind of illusion. And I just want to explain you briefly how that is done in vision. So here's a recreation of that situation. You're moving your eye, and there's a background, a number of dots. So what you're having is an estimate of the velocity of your eyes, basically, of your whatever target relative to the background, this pursued target. That's indicated here by this likelihood function, this estimate of your eye moving across space. Of course, that estimate is not perfect. If you now integrate your prior knowledge about that's velocity, the world usually is stationary. What you end up with is a percept from your eye movement that is lower than your sensory estimate that you're having here, right? You get biased towards lower velocities. Now the second signal that you're getting is the retinal motion that is here. And the retinal motion, of course, goes in the opposite direction than your eye movement does. It is argued that this one here is more precise. If this is also integrated with this prior, it also gets shifted towards the center, but it's shifted less because the estimate in this modality is more precise than the estimate in that modality. In order to judge whether the world is stationary, simple what you have to do is to basically add those two or subtract those two. And what you end up with is a distribution which is not centered at 0, but now you have this shift in there. Now the prediction from that model is that it should depend on the variance of these distributions. So if you add more noise to either estimating the target velocity or the target motion or the retinal motion, then you should be able to shift around the estimated velocity of the target background. There's another illusion, and I'll tell you about that, because that's a little bit more simple to measure those two, namely basically to measure those two intervals independently. In the Fellaini illusion, we measure those two together, because you show a background and the target and the background and the target at the same time. You can show them also sequentially. You can first show an eye move, or first show the object motion, which is motion, for example, in this direction. And then in the second interval, you have no object motion, but you have eye motion, like this. And then you ask whether the second interval, the eye motion, or the object motion, which one was faster. And what you get is basically the same kind of gain factors, and you can show that basically both illusions are pretty much related to one another. Now this is for us experimentally much easier, or not easier, but it's easy to manipulate as well. So we can use our device again here in order to have two intervals. The first interval is tactile motion. So here you just put your finger there while the belt is movement. And the second interval is kinesthetic motion, so there's no tactile motion. You're basically following that the belt here for a while. And then we have four different conditions that we test, namely kinesthetic against tactile, or tactile against kinesthetic. Those we can use to measure the point of subjective equality, so this gain factor that you have in there. Or we do a measurement between kinesthetic and tactile. Those we can use to measure the difference in the discriminability, so how much noise is there in each of the two estimates in there, in order to fit the model. Okay, so first of all, to show you that this illusion is basically the same as the Fellaini illusion, this illusion is called the Aubert-Fleischl phenomenon, or Aubert-Fleischl illusion. And you basically get the same kind of illusion. The reference was here at 6. And if I measure kinesthetic versus tactile, I get a shift in the point of subjective equality going down. If I measure tactile kinesthetic, the shift goes up in the opposite direction. So it's the same kind of illusion, just with a sign change. This here is again an individual subject. Here's the group data, and again, against the reference, you basically have the same effect for 9 participants. Quite interestingly, if we look at the J and Ds, they don't much differ. So from what I already told you about this model, it seems the Bayesian model, they would need to have a difference between these two estimates in order to predict a change in the gains, which here is not the case, but I'll come back to that point in a second. Okay. So we want to test the first prediction, namely, does it depend on spatial frequency in there? So what we did, we used, and basically we created belts of different spatial frequency, which we can, well, it was actually that easy to find them, but we had a shop which made belts for us with different spatial frequency. It was either a smooth belt, a belt with low spatial frequency, or a belt with a high spatial frequency. And what we find is, this is the data I've basically shown you before with a high spatial frequency. There's a huge effect with high spatial frequency, which decreases and goes away with the smooth belt. So if there's no spatial frequency, or it's very smooth, then the effect goes away. So, and that's analog to vision. In vision, you find the same thing. When you basically have only an edge that is moving, which basically compares to a smooth surface, then you don't have any illusion. If you have low spatial frequency, you have a little bit of illusion. If you have a high spatial frequency, you have the maximum of the effect. So it's certainly not a fixed gain. The gain varies with spatial frequency. The other prediction that the Bayesian model makes is it should depend on the relative precision between the retinal and the external retinal signals in vision. So if we translate that to touch, it should be the motion of the hand and the tactile motion that we get on the finger. So this, just taking, I've explained you the model. We can take the model into the touch domain by saying, well, you go over the surface, but keeping the stationary condition, or the tactile motion doing them. If there's a difference between the likelihood function and you have the same prior involved, then you should get this difference in the illusion. Okay, this is the data I've shown you for the PSE shifts. This is the difference in the JND. This was the data, again, that I've showed you before. There was basically no difference in the JND. If we lower the frequency, there starts to be a slight difference. On the smooth surface, there is a difference between those JNDs. So to make this a little bit more clear what is going on here is we plotted the gain factor that we have for the illusion against the difference in the JND and color-coded the different conditions, the smooth belt, the low spatial frequency, and the high spatial frequency. And what you can see is that there's a nice correlation. So basically, both factors clearly play a role. It's a dependency on the spatial frequency, so this gain model seems to have something clearly going on. But it's also the dependency on the difference in the JND, which is predicted by this base model. The base model would predict that these data should lie down here. They should go down through 0, 0. Why they don't, we don't know at the moment yet. We still have to figure out why that is the case. But both models seem to have some truth to it. So yeah, with that, I basically can conclude, and I wanted to show that, yeah, it's sometimes useful to analyze some illusions in the other domain, to come here to haptics and understand something about, in this case, how we put together kinesthetic information and tactile information under reduced situation in this case. These illusion and vision, they go away if you have full field of view. And I guess in touch as well, if you go over a surface for a longer time, you have no problem figuring out where the surface is stationary or not. It's only under these conditions where it's relatively sparse information where we can see the limits of the sensory processing. With this, I conclude. I also want to thank Winston Hayward, who was part of these studies, and of course the EU project THE and Wareham. Thank you.
Thank you very much. We have time for some questions.
Did you think of slanting the ridges?
Slanting the ridges on the subbelt, you mean? We haven't really thought about that. It's not that easy to find these manufacturers who make belts for you that way, the flexible belts which are continuous. But why would you think that would make a difference? Because you have different friction going this way or that way?
I think the perception of the direction of motion would be no longer along the direction of real motion, but would be skewed.
Oh, you mean slanting this way? I see, yeah. I see. Like what you have done with the, yes, now I understand. Your aperture problem, yes, no, I guess so, that's true. You can probably bias the direction of motion, particularly if you then use soap or something like that, you would be able to get a difference in the direction of motion with a slanted belt.
The experiment would be three-dimensional then.
Yes.
Because you have to...
No, that's a good idea. That should be easy to probably manufacture, or more easy than... I thought slanted, you mean each element was slanted.
No.
Yes. Yeah, that's a good idea.
How do you prevent your subjects from listening to the motor and guessing the speed from the sound that it makes?
It's quite easy. We give them headphones and play very loud, white noise basically, or pink noise or something like that. It's very annoying to them, but they don't hear anything out there anymore. But yeah, it's certainly something to consider, that there's no other cues than tactile cues. Of course, they're also blindfolded and everything, so they don't look at the belt.
So we've done this study with Astrid, where instead of looking at motion of the finger on the surface, you may remember the subject exerts static forces, but in opposite direction. Mm-hmm. And when they're asked to reproduce those fingertip positions, they put them in a way that reflect what the fingers would have been had zero friction on the surface. I wonder whether
people would misjudge the location of their hand.
Yeah, because one thing that made me think about is when you said that the illusion probably would disappear if you had a larger a larger contact area. In our case, it happens to be that we just looked at fingertips of thumb and index finger.
Yeah.
And so we thought that maybe subjects are just, predicting where the fingers would have been, and then, that bias in the perception. But I wonder whether be a subgroup of...
Well, the question is, what do they attribute that, whatever, since the way we asked them is basically for the surface, that wouldn't be, so they had to judge their finger velocity correctly. But of course we could ask them the other way around, is ask them for their perceived hand motion. Maybe you find a slight effect on the hand motion as well, and this would predict then a change in the finger position over time. It could well be. That's an interesting thought. I haven't thought about that really to look at that. But yeah, there are certainly several illusions where you can look at misperception. Localization in touch is actually, from proprioception, is quite terrible. We've done several studies in this direction as well, showing how terrible that is. So I can easily think that, yeah, especially during motion, you can easily fool the system where the hand actually is perceptually. That it works.
Okay, any more questions? Okay, let's thank Mark again.
Okay.
Talk. So the next speaker to introduce is rather easy for me. Is my former colleague and office mate Sami Haddadin, who moved to Universität of Hannover early this year, in this leading the Institute of Automatic Control. Automatic Control, and he will present his work on robots for humans.
Okay, works. Awesome. All right, so thanks a lot for the introduction, Thomas, and thanks again for inviting me here and also for the wonderful morning where I saw very nice PhD thesis defenses. So since I just started basically in Hanover, and I've been at DLR for quite some time, so I really want to point out that many of the things that I'm going to show today have been work that I've been doing during my time at DLR together with all the colleagues that have been working there with me and I could work with. And also we're collaborating currently more and more and having some new insights there. So robots for humans, what does this mean? So it's a little bit of different topic than the THE project itself. So I just tried to make a quick run through the topic so that we can go to, to dinner and maybe I can stay below the 20 minutes then. So basically what I've been working on a lot over the last years is how can we design and control robots that are just being, the whole purpose is basically to share the workspace with humans, and how can they safely, intuitively collaborate with them. And Asimov's first law has been kind of my goal with the research that I've been pursuing in order to basically not hurt other humans and myself during all these I've been doing so far. And it's kind of the line of research that we try to kind of bring human-robot interaction in the sense that that human-robot interaction is kind of the extension of all the human-computer interaction that we have in our everyday environments, going into some very basic physical interaction between technological systems and humans, and finally finding their way into basically having a physical agent, namely the robot, that is now very closely interacting with humans, and showing also an active physical response. And this is not only happening in research labs, but also due to the last year, due to the technology transfer that has been going on all over the world, and developing new types of robots that are capable of interaction, bring basically the, let's say, classical stiff design one step further towards robots that are capable of physical exchange of forces and being safe around humans. So basically coming closer to the vision that we have in robotics of close human-robot coexistence and collaboration in everyday environments. And one important step towards such new domains is basically getting robots out of the industrial manufacturing sites, or let's say out of the cages that they have been working on, and letting them do tasks, letting them do tasks that require a sense of touch, a notion of what exact forces do they exert on the environment, and basically solving manipulation and assembly tasks in the real world. So this is just an example of the early work that Daimler has been doing with the KUKA lightweight arm that was originally developed at DLR. So this whole compliance issue and the compliance paradigm, in the morning we also saw very nice presentations of Manolo and Arash, in the sense that active compliance and lightweight design are the key in order to reduce the mechanical impedance of our devices, and torque control and the extension of torque control, basically having passive intrinsic compliance, are the key to building robots that are not only, let's say, soft and interactive in a sense, but also capable. However, this of course requires a lot of effort in the control domain, as we saw today again in the talk of Manolo with the optimal control theories that have been applied to passively compliant robots. So this whole paradigm shift of building soft robots that are capable of interaction has not only been pursued in manipulation and, let's say, arms and hands, but also in whole humanoid designs, such as the IIT Coman robot, the NASA Valkyrie, and also the DLR hand-arm system, which is of course also co-funded by in the THE project, have been some of the major cornerstones in this kind of paradigm shift in bringing intrinsic elasticity into robotic systems, and thus prepare them for basically invading human spaces in terms of compliance. And the origins, at least to my understanding, are the early ones, the MIA design at Zugano's lab at Waseda University, where they basically already introduced a sense of variable stiffness actuation into the design, though being basically before the motion, the compliance of the robot could be changed. And also the seminal work on SEA at MIT by Pratt and Williamson. Then in the beginning of 2000s, I think 2001, 2002, Antonio was kind of being the pioneer in bringing variable impedance actuation into the game and really pursuing the whole extending the whole kind of active compliance control and active impedance control by basically embedding these devices or these designs into the mechanics of the robot. And also in Stanford at Osama's lab, there were new designs emerging that kind of tried to embody compliance and impedance into the mechanical design and complemented only by active control. So this kind of design, however, introduced fundamentally new problems to control, and this is exactly what we saw in the morning as well. So compliant systems have a new kind of energy storage mechanism, which is the elastic spring in the drivetrain. So we can store and release energy by appropriate excitation motions, and what also in Pisa and during my time at DLR we chose as a design tool, and I think also Aline pointed that out earlier, was the theory of optimal control, in order to show basically that in principle, if an elastic robot can drive on the motor side with a certain velocity by appropriate excitation trajectories, you can in fact increase the link side velocity, q max, by a significant amount that mainly depends on the energy that you can basically store on the joint. So basically what we have is a new dimension of control that makes it possible to not only treat the classical tracking problem and regulation problems, but also to try to find a new way in manipulation how we can excite elastic systems such that we can produce novel types of motion. So the whole aspect of dynamics is becoming a new dimension, in the sense that we do not only treat rigid body systems, but also elastic systems where we can have a look at, or where we need to investigate different kinds of energetic sources and basically to control the system such that we can make use of that. And some work we have been doing there is kind of formulating optimal control problems that kind of language that are sought to basically solve certain tasks, and you can do that, which takes quite some time to basically solve these problems. So you can, for example, execute high dynamic motions such as throwing a ball at high speed with a hand-arm system, and this took about half a day to a day to compute the trajectories. However, if you want to build a robot that is designed for human spaces and that can make use of all these elasticities and this energy storage, then the question is, how can you make this knowledge, how can you make these control strategies available in an online fashion? So we came up with basically using optimal control as a tool of exploring the dynamics of a system, and then using dynamical movement primitives, as we saw earlier in one of the talks, in order to encode optimal trajectories into a dynamical system, and then making possible to exploit basically highly costly dynamic optimal control trajectories in order to adjust to certain environmental conditions. So in order to fully exploit the system, we need to basically make this knowledge of dynamics and elastic energy storage mechanisms available in an online fashion. So here in this experiment, we were able to execute these throwing trajectories online by basically seeing where the object or where the target bin is and execute the trajectories instantaneously. So the idea was basically to combine optimal control with let's say, learning algorithms we're using in robotics nowadays, originating from the work of Eisbeth and Schall. And the nice thing is that you can extend the theory to basically any kind of system. So the paradigm itself is basically using optimal trajectories that exploit dynamics and match them together with some learning schemes in order to generalize very costly trajectories in real time by appropriate learning algorithms. And we were able to, I think it was this ICRA, we were showing the results together with, so the PhD student who's doing that is Theodor Tomic from DLR, basically extending to highly acrobatic point-to-point motions to perching, so in high speed, and generalizing these things actually on systems such as quadrotor and micro-aerial vehicles, and being able to exploit also their system dynamics in an online fashion. So this is one of the things that I believe is very important to actually have robots in our space, is not only to be safe and intuitive, so we had the discussion in the morning, I guess, but also productive. We need to be dynamic if we want to, so we need to make dynamics control available in real time, basically. So to sum up, if we want to have a robot in our world, then of course it's nice to have a robot that is safe next to me, but at the same time we really want to emphasize also that it's supposed to be dynamic, to be effective, to be, if it goes to market, it needs to be generating revenue, basically. However, now I want to focus on the two aspects of sensitivity and safeness. So how can we make robots sensitive and safe at the same time? And at DLR there was, of course, the long history and long tradition on impedance control, torque-controlled robots, and Aline has been working since the beginning of the 90s on making these robots perform as they do nowadays. And the final result was the DLR Lightweight Robot 3, which was then technology commercialized to KUKA and can now be bought by everyone if they are able to supply it. So one of the further aspects that you need to take into consideration is not only this compliance and interaction control, so that you can have impedance control with the robot and directly exchange forces, but also be able to detect contacts along the entire structure and react to them appropriately. So you want to basically detect and react to a collision in no time, so hopefully within a few milliseconds, and switch to a reactive strategy. So what we have been doing there was, together with Alessandro De Luca from University of Pisa, a momentum-based collision detection scheme. Oh, Alessandro is not here, right? He's in Rome, of course. I'm speaking too fast to save the dinner, basically, so I forgot where he is. Okay, but together with Alessandro in Rome, and we're still writing our transactions paper since 10 years now, almost, and we're going to submit it presumably 2018, I guess. So, however, the idea was basically to develop an algorithm that is applicable to many different systems, and not only to the lightweight robot, but we applied it also to the Miro system at DLR and also to the hand-arm system. So it's a pretty general algorithm that is able to estimate the external forces acting on the robot in pretty good accuracy and with pretty high bandwidth. So you've got an estimation of the external torques acting on the robot at rather high bandwidth of approximately 20 to 40 hertz on the lightweight robot. And the interesting thing is that you can generalize this whole theory also to flying systems again. So I somehow got interested into this whole flying things. I don't know how this happened, but interesting to know, can actually extend the theory pretty straightforward to flying systems, and basically have exactly the same idea running. Why is this not working? Yeah, running on flying systems, so we can basically detect and react contacts and have interaction control. This is not supposed to be like that, right? So no interaction control. But if we use the same techniques, we can basically apply them to flying systems and detect instantaneously collisions without any additional bumping sensors or things like that. So we just need an inertial model of the system, and then we can basically detect at different speeds to the robot and even extend impedance control to these systems. So what we see here are different strategies, so reflex strategies that basically either stop the robot or you set the equilibrium point, if you want to say so. So the equilibrium point hypothesis and impedance control applies here as well to the robot. We can do inertia shaping. If you estimate the external forces, you can make your systems appear lighter or heavier if you like. And you can have Cartesian impedance control being compliant in certain Cartesian directions. So basically the same analogies we have from serial chain manipulators, we can apply them to the system and combine also impedance control with collision detection and, let's say, selective impedance in different directions. Interesting applications for this is basically to make flying systems also interacting with the physical world. And Theo was just having a demonstration at RSS, I think last week was RSS, and showing that the whole thing can be used, for example, for tactile mapping. So here we can see a flying system that builds up a map in a certain direction, but has no idea that here's a chair in the way, basically detects the contact just by its internal model and estimating the external contact range, basically, and replanning then instantaneously. And what you can see is also that the motion is quite slow, and despite you don't need high dynamics in the forces. So it's a pretty sensitive mechanism in order to make these systems more responsive. And then, of course, there's the question, I mean, you can be compliant, you can detect and react to collisions, but the question is, if you would collide into a human, would you basically hurt him? So one of the basic questions that we have been answering over the last years was basically, so I show this video all the time because back then the robot didn't have collision detection. This was actually the former chancellor before Dr. Merkel, and the robot was almost colliding into our former chancellor. And back then we thought everything is dangerous, so we thought we could have killed the chancellor. And I think, Thomas, you were the one on the safety switch, right? Yeah, and he was brave enough not to activate, so I'm happy for that video since 10 years now. Okay, but the question is basically, given that you have a robot and you've got a curvature, you've got tools and so on, so how fast can you move with such a dynamics design in order to not hurt humans? So we did all these experiments. Oh, sorry for that. And trying to understand how dangerous robots are. And we did all these experiments with basically showing that the robots intrinsically are not able to cause so much harm, at least. Brain is still functional. And extended all these analyses also to bigger robots, to sharp injuries, so with cuts, with knives and so on. So we try to understand fundamentally what is the biomechanics between human injury and how can we make use of that in the sense that we can make robots more safe. So how we basically found a mechanism now that tries to unify together. This is actually joint work together with Antonio. So it was back then a master's student working with me several years ago to develop, oh sorry, this takes forever. So to develop basically the theory to make use of all these biomechanical injury data, injury from biomechanics research over the last 30, 40 years, injury research from automobile industry, and we developed basically an algorithm that makes use of all this data and all these efforts that are going on internationally to basically make a robot safe. And the idea is pretty simple. So it combines operational space or reflected inertia at certain points of interest that are safety relevant and combine or relating that to basic injury knowledge. So the idea is basically if you have a collision, then you basically have a mass, velocity, and impact curvature colliding with your biomechanical system, human. And in robotics, we use a lot of dynamics, and we know our dynamics pretty well, and we can basically calculate the reflected inertia, velocity, and curvature instantaneously at any point on the robot. So what we just have to do is basically calculate them for all relevant points in space, relate them to the basic injury data that comes from drop testing, from cadaver tests and so on, and basically shape the velocity of the robot such that we can basically find, given our reflected inertia, the safe velocity of the robot, given the surface and the intrinsic properties of the robot. So the idea is basically a robot can then autonomously shape its velocity according to the curvature of itself and the objects it carries. So the idea here is basically that upwards it should move pretty slow, downwards much slower because this is quite a dangerous object, up again faster, and then again slower on from the upper left to the lower right. So the idea is basically that the robot relates its curvature and its dynamic properties to injury, and therefore you can basically build a dynamics filter that filters all command velocities such that they are intrinsically safe according to all biomechanical injury knowledge. Then the next question is, of course, how do you collide, or how do you not collide with systems in your environment, and how can you make this real-time capable? So you want to basically react in an instantaneous way, and this is co-work together with AB and University of Agder in Norway, and Rico Belda, who's doing his PhD at DLR, is working a lot on that, in basically making real-time collision avoidance and path planning capable of really being combined with all the soft robotics control schemes we have been working on. So how can we make the robot as responsive as humans would be if objects are in the way? And this has been extended also to whole body collision avoidance,
going to show you here. So basically, I'm sorry for that, but yeah, I didn't pay attention. So the robot is basically having a full-scale model of the human, and he's doing full-scale collision avoidance in real time and replanning, and he's using basically an extended version of the so-called circular fields algorithm in order to pre-plan with a multi-agent system several versions of the same algorithm, and then selects basically the best version in order to execute a safe, however still converging path given the human dynamics and its full-scale geometry. So you can also see that the algorithm is really real-time, so the robot itself would otherwise choose the path above the human there. Then the last thing I want to talk about today is basically if we have all these features together, so this is a lot of work from the Safari project, then one of the main questions, if you have robots that are capable of all these interaction schemes, collision detection, reaction, collision avoidance, all these wonderful methods that people are developing all over the world, then the question is how can we bring this actually into such alignment that the human can make use of that we can use this in robot programming, and how can we tackle this complexity not only on control level but also in programming level. And some work we have been developing over the last years, and that was just and that was just accepted at AAAI, is basically a human collaborative planning algorithm that, given a certain assembly tasks, it basically distributes the particular task to the human robot in order to basically exploit the inherent capabilities of each agent such that you can optimally combine them given the respective assembly plan. So we basically combine the capabilities of humans and robots in order to execute certain tasks. And the idea here was basically to show that for a toy example, so in an assembly toy train, we can basically collaboratively plan these actions with two robots acting as two agents. We have all these features such as collision detection, collision reaction, interaction schemes, and so on. And the robots then dynamically execute and replan the actions in real time. So this was one of the main premise. So we basically combine certain global planning schemes for distributing the task and having a nominal plan such that during the interaction with the human, that can be basically chaotic, right? Many humans are chaotic, as am I. They can do all kinds of things in order to disturb robots. Especially if you go to Automatica or some fair, you would wonder how humans want to disturb robots. So we basically try to to combine global planning with local replanning in order to find the way again into the task and combine all these things together. So maybe I just switch to the planning. Yeah, here you can, for example, see how you can stop, replan, restart the task such that it's still being fulfilled. And the idea is here that the robots basically feed the human that here builds the toy track. So there is a given plan of an assembly, and the robots then fulfill their respective action plans in order to support the human such that he's able to do all these things. And during this execution, the robot is always able to interact with the human and being stopped, for example, due to touch. So he's able to detect a contact and react such that it's either interaction or it is a kind of reflex reaction that is supposed to increase safety. So here you can see some haptic interaction with the human and the robot. So depending on from which side you basically push, the robot reacts in a different way. And I think the next thing I just want to show last is, no, wait. If there's a pretty heavy collision, which you see here, then the entire, no, that's not true. Where is it? The long video. Okay, oops, wait. No, that's the last one, right? I told you. Okay, the task is being restarted, and now, okay, I'm somehow missing the point, but there's supposed to be some interaction going on. Oh yeah, severe collision, the entire cell stops. So the idea is basically to have all these multi-level controllers that basically try to make use of the proprioceptive sensing and basically having replanning in real time such that robots and humans can work together despite all the inaccuracies that the human brings into the game. Okay, and now I don't want to be the last one talking too much, so I just want to show something I'm particularly proud of. World champion, thank you very much. Thanks.
Okay, thank you very much, Sami. I'm sure there is some questions.
Everybody's hungry, come on.
Okay, I have a quick question. So you are applying the things to robot arms, to multiple robot arms, to flying robots. What is the next type of system you're applying these algorithms?
That's a good question. Humanoids, how about humanoids? Yeah, humans. So Etienne and myself, we want to apply it to humans, right?
Well, I have a question about the flying. This.
Yes, sure.
Did you try to make collisions with dynamic flying objects? I mean, you made tests only with wall. So can you imagine if they collide two flying robots?
Two flying robots?
Yes.
Okay.
Well, I mean,
yeah, sure. In principle, it should work. Yeah. I mean, there's nothing that prevents. The theory would say it works. Yeah. But do you mean whether it's a flying object? So
yes,
actively flying.
Yes, actively flying. Yes.
And both retract, or?
Well, one of them reflects.
Okay, if one retracts and the other chases, then they collide again, I guess. But in principle, the theory does not have any assumption on the environment. So basically, the idea is to monitor the dynamics and the state of the system, such that you get an estimation of the external forces. So there's no assumption on stiffness of the environment or anything like that. Nothing. It's purely assuming that you know the dynamics and the state of the system. That's it. And you can show that. In fact, what you can show is that you can get an estimation of the external contact range, which is 6-dimensional. That is just a low-pass filtered version of the true external forces, which is a result that we got together with Alessandro, and he actually did it before for serial chain manipulators. So exactly the same theory applies there. So no assumption on what you collide into. Yeah. Yes, yes. It's a passive estimation. It's a low-pass filtered version. Yeah, exactly. That's the application.
Kite fights, right?
Yeah, like a cat fight. That's the, yeah. I'm not so sure how much do they cost, these systems, right? So it's a costly experiment we would do there. But in principle, yeah. Yeah.
Okay, let's thank Sami again for his
Thanks
talk.
a lot.
And let's thank all the speakers during the session. Thank you.
Well, it's after 7 o'clock, so I think everybody wants to go. So I'm told that closing remarks should always be as brief as possible. So what I wanted to say was I'm sure the rest of you will agree with me that today has been a wonderful day. Brought together some really great research, some really great researchers, and we've all had a great experience. Antonio started this event, I guess, 4 years ago, is it, Antonio? And it started essentially, he had the PhD vivas, and then the people who were actually on the committee were often asked to make some presentations. This has gradually grown. This year it's turned into much more. It's more a mini conference, or maybe even a full workshop. I think it's very impressive. I'd like to thank all of the speakers. I think the audience would, if you join me in thanking all the speakers, this was a really excellent day. I'd like to thank all the people in the audience. I think, again, this surprised Antonio. Last week, I sent an email from IIT saying we had about 20 people that wanted to come along. Was it okay? And he said, yes, I think we'll try and find a bigger room. This morning he said there were over 100 people had registered. And I think counting around just in this room today, there are certainly very close to 100 people at this minute. There will be other people online, so we have had a great turnout. I know that people from IIT were coming to me and actually saying that they really wanted to go to this. So that, again, is a testament to the quality of the presentations. And finally, I'd like to say a big thank you, or like us all to say a big thank you to Antonio and to his team here. I think this has been really well organized. I think it is something that I hope will continue. Everything has been perfect. Well done, Antonio. And I think that's it. We should go and get something to eat.